Hello there, and welcome to the Sleepwalk Space. I'm so glad you found your way here tonight. Maybe you're curious about the cosmos, or maybe you just need something gentle and fascinating to ease you into sleep. Either way, you're in the right place. Tonight, we're exploring 101 facts about our home galaxy, the Milky Way. A vast spiral of stars and secrets spinning through space. You don't need to remember every detail. Just let the words wash over you, let your mind drift where it will, and allow the wonder of the universe to carry you softly toward rest. If these cosmic explorations help you unwind, consider liking and subscribing. It helps others find their way here too. Now, let's begin our journey through 101 facts about the Milky Way galaxy. Fact 1. The Milky Way is a barred spiral galaxy. When astronomers look at our galaxy's structure, they see not just spiral arms, but a thick bar of stars cutting across the center. This bar stretches tens of thousands of light years and rotates slowly, funneling gas toward the core and shaping the inner spiral arms. It's a common feature in spiral galaxies, a backbone of stars that gives our galaxy its distinctive architecture. The bar itself is made up of billions of stars moving in elongated orbits, creating a dense river of light that flows through the galactic center. The structure wasn't always known. For many years, astronomers debated whether the Milky Way had a bar at all. Our position inside the disk made it difficult to see the full structure, but infrared observations that could peer through the dust revealed the truth. A prominent bar dominates the inner galaxy, rotating at its own pace, slightly offset from the spiral arms themselves. The bar serves an important function. It acts like a cosmic highway, channeling gas from the outer disk inward toward the center where it can fuel star formation or feed the supermassive black hole lurking at the core. Without this bar, the dynamics of the inner galaxy would be completely different. The flow of matter, the distribution of stars, and even the shape of the spiral arms all depend on this central structure. It is one of the fundamental architectural features that makes our galaxy what it is. Fact 2. The galaxy contains between 100 and 400 billion stars. The exact number is uncertain because many stars are too faint or hidden behind dust to count directly. But current estimates suggest somewhere between 100 billion and 400 billion suns shine within the Milky Way's bounds. Each one a world of nuclear fire, each one with its own story written in light. Think about that number for a moment. Even at the lower estimate, 100 billion stars means that if you could count one star every second, it would take you over 3,000 years to count them all. And many of these stars are not solitary like our sun. They exist in binary pairs or even larger multiple star systems. Some are massive blue giants burning through their fuel in mere millions of years. Others are tiny red dwarfs that will smolder for trillions of years, outlasting the current age of the universe many times over. The uncertainty in the count comes from multiple factors. Faint red dwarfs are incredibly difficult to detect, yet they may be the most common type of star in the galaxy. Brown dwarfs, failed stars that never quite ignited fusion, occupy a gray area between stars and planets. Should they be counted? Then there are the stars hidden in the galactic bulge, obscured by so much dust that we can barely see them even with infrared telescopes. And in the outer halo, ancient stars drift in isolation, so spread out that surveys miss many of them. Every new study refines the estimate, but the true number remains elusive. What we know for certain is that the Milky Way is densely populated, a city of suns spread across an incomprehensible volume of space. Fact 3. The Milky Way is approximately 13.6 billion years old. Our galaxy formed not long after the Big Bang itself, taking shape when the universe was still in its infancy. Over those billions of years, it has grown, changed, and evolved into the spiral we inhabit today. It carries within it the memory of cosmic dawn. The earliest stars in the Milky Way formed from nearly pure hydrogen and helium, the only elements created in the Big Bang. These first generations burned bright and fast, fusing heavier elements in their cores and scattering them into space when they died. Each subsequent generation of stars formed from slightly enriched gas, building up the periodic table element by element, supernova by supernova. The galaxy itself took shape gradually. In the beginning, there was no disk, no spiral arms, just a loose collection of gas clouds and protogalactic fragments falling together under gravity. These merged chaotically, their stars scattering into a roughly spherical halo. Over time, the gas settled into a rotating disk, flattened by conservation of angular momentum. The first stars are now ancient relics, some still visible in the halo, their compositions marking them as survivors from the earliest epochs. By studying the ages of different stellar populations, astronomers can reconstruct the galaxy's history, piecing together a timeline that stretches back nearly to the birth of the universe itself. We live in a galaxy that is old, mature, and still evolving, still making stars, still changing its shape across the vast canvas of cosmic time. Fact 4. The galaxy spans about 100,000 light-years across. From one edge of the disk to the other stretches a distance so vast that light itself takes 100,000 years to cross it. To put that in perspective, a beam of light leaving one side of the galaxy today won't reach the other side until long after our civilization has risen and fallen many times over. If you could shrink the Milky Way down so that the distance from the Sun to the nearest star, about 4 light years, was compressed to the width of your hand, the entire galaxy would still span a region larger than a city. The scales involved are genuinely difficult for human minds to grasp. We evolved to understand distances we can walk, spaces we can see across, times measured in human lifetimes. But the galaxy operates on scales millions of times larger. Light from the galactic center takes 26,000 years to reach us. That means when we look toward the constellation Sagittarius, we're seeing the core as it was 26,000 years ago, long before human civilization began. Events happening there right now will not be visible to us for another 26 millennia. And this 100,000 light-year span is just the visible disk. If we include the dark matter halo, the sphere of invisible mass that surrounds and permeates the galaxy, the true size may extend several 100,000 light-years. The Milky Way is not a small, cozy home. It is a vast island universe unto itself, containing more stars than you could ever count, more worlds than you could ever visit, more stories than could ever be told. Fact 5. Our solar system is located about 26,000 light-years from the galactic center. We orbit in what astronomers call the galactic suburbs, far from the crowded, dangerous core. It's a comfortable distance, neither too close to the chaos nor too far from the richness of the spiral arms. A quiet neighborhood in a busy galaxy. If you imagine the Milky Way as a vast city, we live in a peaceful residential area, not in the dense urban center where stars crowd together and supermassive black holes lurk. but not in the sparse rural outskirts either. This location has probably been important for life on Earth. Closer to the center, the density of stars is much higher. Gravitational interactions are more frequent. Supernova explosions happen more often, bathing nearby systems in deadly radiation. The supermassive black hole itself, though currently quiet, may have been much more active in the past, flooding the inner galaxy with high-energy light. Out here, things are calmer. Stars are more spread out. We orbit at a steady pace through a relatively empty region of space. The nearest star to us, Proxima Centauri, is still over 4 light-years away. That enormous distance, which seems vast on human scales, is actually quite typical for stellar separations in our part of the galaxy. We have room to breathe. We're not constantly disturbed by close encounters or cosmic catastrophes. This may be exactly the kind of stable, quiet environment that complex life needs to evolve and thrive over billions of years. Fact 6. The Milky Way's disk is about 1,000 light-years thick. Though it spans tens of thousands of light-years across, the disk is remarkably thin, like a plate spinning through space. Most stars, including our Sun, orbit within this flat structure, creating the luminous band we see stretching across the night sky. The thinness of the disk is a direct result of how galaxies form. When gas clouds collapse, under their own gravity, they spin. And when spinning clouds collapse, they flatten into disks, just as a blob of pizza dough flattens when you spin it in the air. Conservation of angular momentum requires this. The gas can easily fall inward along the spin axis, but in the plane of rotation, centrifugal force balances gravity, creating a stable disk. The stars in this disk orbit in roughly circular paths, all moving in the same general direction like cars on a racetrack. But the disk isn't perfectly uniform. It's actually composed of 2 main components. The thin disk, where the Sun lives, is rich in gas and actively forming stars. It's typically only about 1,000 light-years thick. Above and below it lies the thick disk, a more diffuse layer of older stars on slightly more elliptical orbits. These stars puff out to create a thicker layer, perhaps 3,000 light-years from top to bottom. Beyond that lies the halo, a roughly spherical distribution of ancient stars and globular clusters. From our vantage point inside the disk, when we look along the plane, we see the accumulated light of billions of stars creating that luminous band across the sky. When we look up or down, perpendicular to the disk, we see out of the galaxy into the dark space beyond, with only the scattered stars of the thick disk and halo in our line of sight. Fact 7. At the center lies Sagittarius, a star, a supermassive black hole. This monster contains more than 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Though it appears quiet now, it exerts tremendous gravitational influence on everything nearby, holding the inner galaxy in its invisible grip. For many years, astronomers suspected that a massive object lurked at the galaxy's center, but they couldn't see it directly. Black holes emit no light. They can only be detected by their gravitational effects on nearby matter. So, researchers watch the stars closest to the galactic center, tracking their orbits year after year with painstaking precision. What they found was astonishing. Stars near the center move incredibly fast, some whipping around at thousands of kilometers per second in elliptical orbits. By measuring these orbits, astronomers could calculate the mass of the object they were orbiting around. The answer was unambiguous. more than 4 million solar masses concentrated in a tiny volume. Nothing but a supermassive black hole could create such powerful gravity in such a small space. This discovery earned the 2020 Nobel Prize in Physics. Sagittarius, A star, as it's called, sits quietly at the heart of our galaxy. Occasionally, gas or dust strays too close and is heated to extreme temperatures as it spirals inward, producing brief flares of X-rays and infrared light. But most of the time, the black hole is dormant, starved of material. If you could somehow watch it from a safe distance, you would see stars looping around an empty point in space, their orbits defining the presence of an invisible monster. This black hole has probably been at the center of the Milky Way since the galaxy formed, growing over billions of years by consuming gas and stars, helping to shape the structure and evolution of the entire galactic core. Fact 8. The galaxy rotates, but not like a solid object. Different parts spin at different speeds. Stars near the center complete their orbits much faster than those farther out. This differential rotation creates the spiral pattern we observe, a dynamic swirl of stars and gas constantly reshaping itself across cosmic time. If the galaxy rotated like a solid wheel, with all parts turning at the same angular speed, the spiral arms would wind up tighter and tighter over time until they were completely wrapped around the center. But this doesn't happen. Instead, the spiral arms persist because they're not made of specific stars that stay in the arms forever. Rather, they're density waves, patterns that move through the disk at their own speed. Stars and gas drift into these regions of higher density, slow down slightly as they pass through, then drift out the other side. It's like a traffic jam on a highway. The jam itself moves slowly backward relative to traffic flow, even though individual cars pass through it and continue on. In the same way, spiral arms move through the galaxy, and stars flow in and out of them. This differential rotation also means the stars at different distances from the center have different orbital periods. Near the center, stars might orbit in just a few million years. Out where we are, it takes 225 to 250 million years. Even farther out, in the sparse outer disk, stars take even longer. This creates a complex, ever-changing dance of stellar motions, with the inner galaxy racing ahead while the outer regions lag behind, and the spiral pattern moving through it all at its own stately pace. Fact 9. It takes our solar system about 225 to 250 million years to orbit once around the galaxy. This vast cycle is called a galactic year. Since Earth formed, we've completed only about 20 trips around the Milky Way. The dinosaurs lived during a different galactic season than we do now. Try to imagine this timescale. A galactic year is so long that entire epochs of Earth's history fit within a single orbit. The last time the solar system was in this part of its orbit, roughly 225 million years ago, the supercontinent Pangaea was just beginning to form. The first dinosaurs had not yet evolved. Life on Earth was recovering from the Permian extinction, the worst mass extinction event in our planet's history. Since then, the continents have drifted apart. Life has diversified. The dinosaurs have risen and fallen, and humans have emerged, all within one circuit of the galaxy. And when we complete our current orbit and return to this same position again, another 225 million years from now, Earth will be utterly transformed once more. Perhaps our species will still exist in some evolved form. Perhaps we'll have spread to other star systems. Or perhaps will be long extinct, replaced by new forms of life adapted to a changing world. The galaxy keeps time on scales so vast that human history is barely a flicker. All of recorded human civilization from the first cities to the present day represents only about 1/50,000th of a galactic year. We are newcomers here, brief sparks in a galaxy that turns with ancient, patient rhythm. Fact 10. The Sun travels at roughly 828,000 kilometers per hour through the galaxy. That's more than 230 kilometers every second. And yet, despite this incredible speed, the galaxy is so enormous that our orbit takes hundreds of millions of years to complete. Speed and scale both beyond ordinary comprehension. To put this speed in perspective, it's about 650 times faster than a bullet from a rifle. We are hurtling through space at velocities that would seem impossible to us if we were aware of them. But everything around us, the other stars, the gas clouds, the planets, all move at similar speeds. We're like swimmers in a vast river, all carried along by the same current. So we don't notice the motion relative to each other. This speed isn't just the Sun's orbital velocity around the galactic center. The Sun also bobs up and down through the galactic plane, oscillating like a cork on water. It has a small velocity component perpendicular to the disk, carrying it above and below the midplane on a cycle that takes tens of millions of years. And on top of all this, the entire galaxy is moving through space. We're falling toward the Virgo cluster, pulled by the gravity of thousands of galaxies beyond our local neighborhood. And the local group itself, containing the Milky Way and Andromeda and their satellites, is being pulled toward an even larger structure called the Great Attractor. Motion upon motion, velocity upon velocity. We are in constant movement through the cosmos, sweeping through space at speeds our ancestors could never have imagined, tracing out paths through the galaxy that will not repeat for hundreds of millions of years. Fact 11. The Milky Way is surrounded by a massive dark matter halo. This invisible structure extends far beyond the visible disk, outweighing all the stars, gas, and dust combined. We cannot see dark matter directly, but its gravitational effects are unmistakable. It holds the galaxy together and shapes its motion through space. When astronomers first measured how fast stars in the outer galaxy were orbiting, they found something impossible. According to Newton's laws and Einstein's relativity, objects farther from a central mass should orbit more slowly. This is true in our solar system. Mercury zips around the Sun quickly, while Neptune crawls along at a much slower pace. But in the Milky Way and in other galaxies, the rotation speed stays roughly constant even far out into the disk. Stars in the outer regions orbit just as fast as those closer in. This should not happen unless there is much more mass present than we can see. The solution is dark matter. An enormous halo of invisible mass surrounds the galaxy, extending perhaps 500,000 light years or more into space. This dark matter doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. It only interacts through gravity. But there's so much of it that it dominates the galaxy's mass. The stars, gas, dust, and planets we can see, all the luminous matter makes up only about 10 to 15% of the total mass. The rest is dark matter, invisible scaffolding that holds everything together. Fact 12. Dark matter makes up about 90% of the galaxy's total mass. All the stars we see, all the nebulae and planets and dust, account for only a small fraction of what the Milky Way truly contains. The vast majority is hidden, felt only through gravity, one of the deepest mysteries in modern science. This is a profound realization. It means that when we look at the night sky, when we admire the beauty of the Milky Way stretching overhead, we're seeing only the tip of the iceberg. The galaxy is mostly invisible. Imagine trying to understand a city when you can only see one out of every 10 buildings, and the other 9 are completely transparent. You could map out the visible structures, but you'd be missing the bulk of the city's architecture. That's our situation with the Milky Way. We can see the luminous matter, but the dark matter remains stubbornly hidden. Scientists have been searching for dark matter for decades. They've built sensitive detectors deep underground to try to catch dark matter particles as they pass through the Earth. They've used powerful particle accelerators to try to create dark matter in the lab. They've searched the sky for evidence of dark matter annihilation or decay. So far, dark matter has eluded all attempts at direct detection. We know it's there. The gravitational evidence is overwhelming, but we don't know what it is. Is it made of undiscovered subatomic particles? Primordial black holes formed in the early universe? Something even stranger? The answer remains one of the great open questions in physics. Fact 13. The galaxy contains enormous clouds of hydrogen gas. These molecular clouds can span hundreds of light years and contain enough material to form millions of stars. They drift through the spiral arms, cold and dark, waiting for gravity to pull them into collapse and ignite new suns within their depths. The largest of these clouds are called giant molecular cloud complexes. They're the most massive structures in the galaxy besides the galaxy itself. Some contain more than 1 million times the mass of the Sun, spread out over vast regions of space. Inside these clouds, the gas is incredibly cold, chilled to just a few degrees above absolute zero. At these temperatures, hydrogen atoms pair up to form molecules, and trace amounts of other molecules appear as well. Carbon monoxide, water, ammonia, and even complex organic compounds have been detected. The clouds are so dense and dusty that visible light cannot penetrate them. From the outside, they appear as dark patches against the background stars, obscuring everything behind them. But inside, in the cold and dark, gravity is slowly working. Here and there, the densest regions begin to collapse. Over hundreds of thousands of years, these collapsing clumps grow hotter and denser until their cores reach the temperatures and pressures needed for nuclear fusion. Then, suddenly, stars ignite. The darkness is pierced by brilliant light. Ultraviolet radiation from the new stars heats and ionizes the surrounding gas, making it glow in vivid colors. Stellar winds push outward, carving cavities and pillars. What was a dark, cold cloud becomes a luminous nebula, a stellar nursery where dozens or hundreds or thousands of stars are born together. Fact 14. Star formation happens primarily in the spiral arms. As gas clouds pass through these regions of higher density, they are compressed, triggering the collapse that leads to star birth. The spiral arms light up with young blue stars, tracing out the galaxy's structure like glowing highways through space. This is why spiral arms are so prominent in photographs of galaxies. They shine brightly with the blue-white light of massive, hot young stars. These stars burn through their fuel quickly, living only a few million to a few tens of millions of years before exploding as supernova. They don't live long enough to drift far from where they were born, so they remain in the spiral arms, making those regions appear bright and blue. Older stars, like our Sun, have had time to drift out of the spiral arms and into the spaces between. The disk is full of these older, cooler stars, but they're fainter and redder, so they don't stand out as much. The result is that the spiral arms look like bright, well-defined features, even though they're actually just regions where the density is slightly higher and star formation is currently active. The process of star formation in spiral arms is beautifully self-sustaining. Gas clouds enter the arm and are compressed. They form stars. The most massive of these stars explode as supernova after a few million years. The shock waves from these explosions compress nearby gas clouds, triggering more star formation. This creates a cascade of stellar birth that lights up the arm. Meanwhile, the arm itself is moving through the disk at a different speed than the gas, so fresh gas is constantly flowing in to fuel new generations of stars. Fact 15. New stars are still forming in the Milky Way today. Though the pace has slowed compared to billions of years ago, the galaxy continues to create stars. In regions like the Orion Nebula, we can watch this process unfold, witnessing the birth of stellar systems in clouds of glowing gas. The Orion Nebula is one of the closest stellar nurseries to Earth, only about 1,350 light-years away. It's visible to the naked eye as a fuzzy patch in Orion's sword, and through telescopes, it reveals itself as a stunning region of glowing gas illuminated by young, hot stars. Inside the nebula, hidden by dust, infrared observations have revealed hundreds of protostars, infant suns still gathering mass from their surrounding clouds. Some of these protostars are surrounded by disks of gas and dust that may be forming planets even as we watch. We are witnessing the birth of new solar systems in real time, or at least in delayed real time, since the light we're seeing left the nebula over 1,000 years ago. Star formation in the Milky Way has been declining for billions of years. The galaxy's peak of stellar birth was probably around 10 billion years ago, when there was more gas available and the rate of mergers with other galaxies was higher. Since then, the star formation rate has been gradually decreasing. Today, the Milky Way produces only a few new solar masses worth of stars each year. That may sound like a lot, but spread across the entire galaxy, it's a relatively modest rate. Still, the process continues. Gas continues to collect in the spiral arms, clouds continue to collapse, new stars continue to ignite. The galaxy is not finished growing. It is simply entering a more mature, less frantic phase of its long life. Fact 16. The galaxy produces about 1 to 2 new stars each year. This may not sound like much, but over millions of years, it adds up. The Milky Way is not finished growing. It continues to convert gas into stars, slowly adding to its luminous population across the vast stretches of time. When you think about it, even this modest rate is remarkable. Each year, enough gas accumulates and collapses somewhere in the galaxy to create 1 or 2 new stellar systems. Each of these systems may develop planets, some of which might be habitable. Over 1 million years, that's 1 million to 2 million new stars. Over 1 billion years, it's 1 billion or more. Even at this slow pace, the cumulative effect is enormous. Of course, at the same time stars are being born, old stars are dying. Massive stars explode as supernova. medium-mass stars swell into red giants and shed their outer layers. Low-mass stars slowly cool and fade. The galaxy is constantly recycling its material, turning gas into stars and stars back into gas in an endless cycle. But the net result, right now, is still slightly positive. More stars are being born than are dying. The total stellar population of the Milky Way is still growing, though the growth rate has slowed considerably from earlier epochs. Billions of years from now, as the remaining gas is exhausted or ejected, star formation will finally sputter to a halt. The galaxy will enter a long, slow decline as its existing stars age and die, with no new ones to replace them. But that future is still unimaginably distant. For now, the Milky Way remains alive with the light of stellar birth, adding new suns to its vast population year after year, generation after generation. Fact 17. Some of the oldest stars in the galaxy are found in the halo. These ancient suns formed over 13 billion years ago, when the universe was still young. They contain almost no heavy elements, revealing their primordial origins. They drift in long, slow orbits above and below the disk, witnesses to the galaxy's earliest days. In astronomy, elements heavier than hydrogen and helium are called metals, even though they include things like carbon, nitrogen, and oxygen. The first stars in the universe were made of nearly pure hydrogen and helium because nothing else existed yet. These stars fused lighter elements into heavier ones in their cores, and when they died, they scattered these newly created elements into space. The next generation of stars formed from gas that was slightly enriched with these metals. And so on, generation after generation, with each cycle adding more heavy elements to the mix. The oldest stars in the Milky Way's halo have extremely low metal content, sometimes less than 1/10,000th, the metal abundance of the Sun. This marks them as very early generation stars, formed when the galaxy was less than 1 billion years old. By studying these ancient stars, astronomers can learn about the conditions in the early universe, about the first generation of stars that preceded them, and about how the galaxy itself assembled from smaller protogalactic fragments. These halo stars move on highly elliptical, often retrograde orbits that take them far above and below the disk. They're like elder spirits of the galaxy, drifting through the outer reaches, carrying within their light the secrets of cosmic dawn. Some of them may even have formed in smaller galaxies that were later absorbed by the Milky Way, making them not native to our galaxy, but immigrants from other ancient systems. Fact 18. Globular clusters orbit in the galactic halo. These dense spherical collections of stars contain hundreds of thousands of suns packed tightly together. Some are among the oldest objects in the galaxy, preserved like time capsules from an earlier cosmic era. They circle the Milky Way like distant moths around a flame. A globular cluster is a spectacular sight. Imagine hundreds of thousands of stars crammed into a sphere, perhaps only 100 light-years across. Near the center of the cluster, stars are separated by distances measured in light weeks or even light days, far closer than the light years that separate stars in our neighborhood. If you lived on a planet orbiting a star in the core of a globular cluster, your night sky would be extraordinary. Instead of a few thousand stars visible to the naked eye, you might see hundreds of thousands, so many that the night would never be truly dark. The Milky Way has over 150 known globular clusters, possibly more hidden behind the dust of the galactic plane. The largest, Omega Centauri, contains millions of stars and may actually be the remnant core of a dwarf galaxy that was captured and stripped by the Milky Way billions of years ago. These clusters are incredibly old, most formed over 12 billion years ago, making them nearly as old as the universe itself. Their stars are ancient, metal-poor, and predominantly red, having long since exhausted the massive blue stars that might have once populated them. Because the stars and globular clusters are so tightly packed, interactions between them are relatively common. Stars can exchange companions in three-body encounters. Collisions, though still rare, are possible. This can create exotic objects, like blue straggler stars, which appear younger and more massive than they should, possibly formed by the merger of two older stars. Globular clusters are laboratories for stellar dynamics and evolution, and they're also beautiful reminders of the galaxy's deep history. Fact 19. The Milky Way has absorbed dozens of smaller galaxies. Over billions of years, our galaxy has grown by consuming its smaller neighbors. These dwarf galaxies were drawn in by gravity, torn apart, and scattered across our halo and disk. The Milky Way is not pristine but composite, built from the ruins of many smaller worlds. In the early universe, galaxies formed hierarchically. Small structures collapsed first, then merged to form larger ones, which merged to form even larger ones, and so on. The Milky Way is a product of this process. It started as a collection of smaller proto-galaxies that gradually came together over billions of years. But the merger process didn't stop once the main structure formed. Small satellite galaxies continued to orbit the Milky Way, and over time, tidal forces from our galaxy's gravity pulled them apart, spreading their stars into long streams. By carefully mapping the motions and compositions of stars in the halo, astronomers can identify these streams and trace them back to their parent galaxies. It's like cosmic archaeology, piecing together the remains of ancient civilizations of stars. One of the most significant early mergers was with a galaxy called Gaia Enceladus, which collided with the Milky Way about 10 billion years ago. This merger was so large that it may have puffed up the galactic disk, heating stellar orbits and creating the thick disk component we observe today. The stars from Gaia Enceladus are still here, mixed into the halo and thick disk, distinguishable by their chemical compositions and orbital properties. In a sense, a significant fraction of the stars we see didn't originally form in the Milky Way at all. They're immigrants from other galaxies, now fully integrated into our cosmic community. Fact 20. The Sagittarius dwarf galaxy is being torn apart right now. This small galaxy is currently being shredded by the Milky Way's tidal forces. Its stars are being pulled into long streams that wrap around our galaxy. A slow-motion collision happening over millions of years. We are witnessing galactic cannibalism in action. The Sagittarius dwarf was discovered only in 1994, despite being one of the nearest satellite galaxies to the Milky Way. It's hidden behind the galactic bulge, obscured by the dense star fields in that direction. But once identified, it became clear that this small galaxy is in the final stages of disruption. It has already made multiple passages through the Milky Way's disk, and each time, more of its stars are pulled away by tidal forces. Long streams of stars from the Sagittarius dwarf wrap around the entire galaxy, looping above and below the disk in intricate patterns. These streams have been mapped using surveys like the Sloan Digital Sky Survey and the Gaia mission. By tracing the streams backward, astronomers can reconstruct the orbit of the dwarf galaxy and understand how it has interacted with the Milky Way over time. Eventually, over the next few billion years, the Sagittarius dwarf will be completely dissolved. Its stars will become indistinguishable from the general halo population of the Milky Way. The dwarf galaxy will cease to exist as a separate entity, fully consumed by our larger galaxy. This is not a violent or explosive process. It's slow and gentle, a gradual assimilation driven by the relentless pull of gravity. But the result is the same. A smaller galaxy is erased, its stars absorbed into the larger structure, adding to the Milky Way's mass and complexity. Fact 21. Stellar streams trace the paths of destroyed galaxies. Across the sky, astronomers have mapped thin ribbons of stars, remnants of smaller galaxies that wandered too close and were pulled apart. These streams wrap around the Milky Way like ghostly threads, evidence of ancient mergers and quiet cosmic violence. Stellar streams are surprisingly common. Dozens have been identified so far, and as surveys become more complete, more are discovered. Each stream represents the death of a smaller galaxy or star cluster, torn apart by the Milky Way's tidal forces. The stars in these streams all move on similar orbits because they originated from the same parent object. They follow the path that the original galaxy or cluster took as it orbited the Milky Way. But now, they're spread out along that orbit like beads on a string. Some streams are thick and prominent, containing thousands or even millions of stars. Others are faint and difficult to detect, visible only in careful statistical analyses of large surveys. The streams can wrap around the galaxy multiple times, creating complex patterns in the halo. By studying these patterns, astronomers can map the distribution of dark matter in the Milky Way, because the exact shape and motion of the streams depends on the gravitational field they're moving through. Stellar streams are also beautiful in their own right. They're cosmic ghosts, the remains of smaller galaxies that once existed as coherent structures but are now dissolved into the larger sea of stars. They remind us that the Milky Way has not grown alone. It has consumed a multitude of smaller systems, each one adding to its mass and diversity, each one leaving behind these delicate tracers of its final orbit. Fact 22. The galaxy's disk is warped, not flat. The outer edges bend upward on one side and downward on the other, creating a graceful S-shaped curve. This warp may be caused by interactions with satellite galaxies or by the pull of dark matter. The Milky Way is not a perfect disk, but a living, breathing structure. For a long time, astronomers assumed the galactic disk was flat. But as observations improved, it became clear that the outer disk deviates from flatness, twisting up and down in a wave-like pattern. The warp is subtle near the sun's position but becomes more pronounced farther out, where the gravitational influence of the central galaxy weakens. The cause of the warp is still debated. One possibility is that satellite galaxies like the Large and Small Magellanic Clouds exert a gravitational tug on the disk as they orbit, pulling it out of alignment. Another possibility is that the dark matter halo itself is not perfectly spherical, and its asymmetries cause the disk to bend. Simulations suggest that a combination of factors is probably responsible. The warp is not static. It rotates slowly, precessing around the galaxy over hundreds of millions of years, like a wobbling plate spinning through space. From a vantage point outside the galaxy, the Milky Way would look like it's gently undulating, with waves moving through the disk over time. This is yet another reminder that galaxies are not rigid structures. They're dynamic, flexible, constantly responding to internal and external forces, always in motion, always changing shape. Fact 23. The Milky Way has a central bulge. At the heart of the galaxy, stars cluster densely into a bright, rounded region. This bulge contains older stars and is shaped somewhat like a peanut when viewed from the side, a three-dimensional structure formed by billions of years of gravitational dynamics. The central bulge is one of the oldest components of the Milky Way. Most of its stars are over 10 billion years old. Metal-rich compared to halo stars, but formed early in the galaxy's history. The bulge contains tens of billions of stars packed into a relatively small volume, creating a dense, bright region at the galaxy's core. The peanut shape of the bulge is a relatively recent discovery, made possible by infrared surveys that can peer through the obscuring dust. The bulge is not a simple sphere or ellipsoid. It's a complex, three-dimensional box or peanut structure, with a thick vertical extent and a narrower middle section. This unusual shape is thought to arise from the central bar. As the bar rotates, stars in it can become unstable and begin moving in vertical orbits, puffing up to create the peanut shape. It's a phenomenon called buckling, where the bar essentially thickens itself over time. The bulge is also home to the supermassive black hole Sagittarius A star. The dense environment near the black hole is extreme, with stars packed so closely that interactions and collisions are relatively common. Some stars orbit the black hole at incredible speeds, whipping around in just a few years. These stars provide a natural laboratory for testing general relativity and strong gravitational fields, and observations of their orbits have confirmed Einstein's predictions with remarkable precision. Fact 24. We cannot see the galactic center in visible light. Thick clouds of dust block our view, obscuring the core from our telescopes. But in infrared and radio wavelengths, the center glows brightly, revealing the dense concentration of stars and the supermassive black hole lurking at the heart of everything. The galactic center lies in the direction of the constellation Sagittarius, low on the horizon for northern hemisphere observers, but prominent in southern skies. When you look toward Sagittarius on a dark night, you're looking toward the heart of the galaxy. But interstellar dust absorbs and scatters visible light, especially blue and green wavelengths. The result is that the central regions of the galaxy appear dim and reddened in optical telescopes, with vast swaths completely obscured by dark clouds. Longer wavelengths, like infrared light, can penetrate the dust much more effectively. Infrared telescopes reveal the galactic center as a bright, crowded region filled with stars. The central parsec, the innermost light year or so around Sagittarius, a star, contains millions of stars, an astonishing density. Radio observations reveal even more. The galaxy's center is laced with filaments and arcs of ionized gas, probably shaped by magnetic fields. Molecular gas clouds swirl in complex patterns. And at the very center, Sagittarius A star itself emits radio waves, flickering and flaring as hot gas spirals into the black hole. Observing the galactic center is like peering through a foggy window. Visible light gives us only a vague impression. But with the right tools, the fog clears, and we can see the bustling, chaotic heart of our galaxy in all its glory. Fact 25. The galaxy has at least 4 major spiral arms: the Sagittarius arm, the Scutum Centaurus arm, the Perseus arm, and the Norma arm all curve outward from the central bar. But the exact number and structure of these arms is still debated. From our position inside the disk, it's difficult to map the full architecture. Mapping the spiral structure of the Milky Way is one of the most challenging problems in galactic astronomy. We're trying to determine the shape of a structure from the inside, which is a bit like trying to figure out the layout of a forest when you're standing in the middle of it. You can see nearby trees clearly, but the more distant structure is obscured and confusing. Astronomers use several techniques to map the spiral arms. They look for concentrations of young, bright stars and star-forming regions, which tend to trace out the arms. They map the distribution of molecular gas using radio telescopes. They measure distances to various objects using techniques like parallax and spectroscopic parallax. But even with all these methods, uncertainties remain. Some studies suggest the Milky Way has 2 major arms and several minor spurs. Others argue for 4 major arms of roughly equal prominence. The arms themselves are not sharply defined. They're regions of slightly higher density that blur into the surrounding disk, and they're not perfect logarithmic spirals. They have kinks, branches, and gaps that complicate the picture. The Milky Way's spiral structure is probably messier and less symmetric than the beautiful spirals we see in face-on images of other galaxies. But from the outside, our galaxy would still appear as a grand design spiral, with clear arms sweeping outward from a central bar, a cosmic pinwheel slowly turning in space. Fact 26. Our solar system sits in a minor arm called the Orion Spur. This smaller feature lies between 2 major spiral arms. It's not as dense or dramatic as the main arms, but that may be fortunate for us. The relative calm of this region may have given Earth the stability needed for complex life to evolve. The Orion Spur, also called the Orion Arm or the local arm, is a small partial arm or inter-arm spur that contains the Sun and many nearby stars. It's located between the larger Perseus arm and the Sagittarius arm. While the major arms are tens of thousands of light-years long, the Orion Spur is only a few thousand light-years in length. Living in a minor arm has its advantages. In the major arms, star density is higher and massive stars are more common. These massive stars live fast and die young, exploding as supernova after only a few million years. If the Sun orbited in a major arm, Earth would be exposed to more frequent supernova, which could strip away the ozone layer and bathe the surface in harmful radiation. The gravitational perturbations from nearby stars would also be more frequent, potentially disrupting the outer solar system and sending comets plunging toward the inner planets. In the Orion Spur, things are quieter. We orbit in a relatively empty region of space, far from the galaxy's most violent phenomena. This stability may have been crucial for life. Complex life on Earth took billions of years to evolve, and it may have required a stable, undisturbed environment to do so. If Earth had been subjected to repeated catastrophic events from astronomical sources, life might never have progressed beyond simple forms. So our location in a minor spur, while perhaps unremarkable from a galactic perspective, may have been just right for us. Fact 27. The spiral arms are density waves, not fixed structures. Stars and gas flow into these regions, linger for a while, then drift out again. The pattern moves through the galaxy like a slow ripple, triggering star formation as it goes. The arms appear permanent, but are actually dynamic waves of compression moving through space. This concept of density waves was developed in the 1960s to explain how spiral arms could persist over time. If the arms were made of the same stars throughout the galaxy's life, differential rotation would wind them up tightly in just a few orbits. But if the arms are patterns, waves of compression that move through the stellar population, they can remain open and well-defined indefinitely. Think of it like the wave that moves around a stadium during a sports game. The wave itself travels around the stadium, but each individual person stays in their seat, standing up when the wave reaches them and sitting back down after it passes. The wave is a pattern of motion, not a physical object. Spiral arms work the same way. As stars and gas orbit the galaxy, they occasionally pass through a spiral arm, a region where the density is slightly higher. The increased density slows them down temporarily, causing them to bunch up. This bunching is what makes the arm visible. As gas clouds are compressed in the arm, they collapse more easily, triggering bursts of star formation. The massive young stars that result light up the arm with their brilliant blue-white light. Meanwhile, the density wave itself continues to rotate through the disk at its own pace, independent of the individual stars. It's a self-sustaining pattern, maintained by the galaxy's gravitational field and its rotation, a beautiful example of collective behavior emerging from simple physical laws. Fact 28. Interstellar dust obscures much of the galaxy from view. Tiny grains of carbon and silicate scatter and absorb light, creating dark patches across the Milky Way's band. What appears empty is often just hidden. Behind the dust, star formation continues unseen until infrared telescopes reveal the glow of newborn suns. Interstellar dust is remarkably effective at blocking light, even though the individual grains are microscopic and the density is incredibly low by terrestrial standards. If you could gather all the dust between here and a nearby star and compress it to the density of sand, it would barely fill a small room. But spread out over light years of space, even this tenuous material absorbs enough light to significantly dim and redden distant stars. The dust grains themselves are complex structures. They're made primarily of silicates and carbon compounds, coated with ices in the coldest regions. They form in the atmospheres of cool stars and are blown into space by stellar winds. Supernovae also create dust grains in their expanding ajax. Once in space, the grains can be further processed by cosmic rays and ultraviolet light, creating even more complex chemistry on their surfaces. Dust plays a crucial role in the galaxy. It absorbs ultraviolet and visible light from stars and re-emits the energy as infrared radiation, cooling the interstellar medium. It provides surfaces where molecules can form, catalyzing chemical reactions that would be nearly impossible in the gas phase. And it shields the densest regions of molecular clouds from stellar radiation, allowing them to collapse into new stars and planets. Without dust, the galaxy would look very different, and the process of star and planet formation might not even be possible. Fact 29. The Milky Way emits light across the entire electromagnetic spectrum. From radio waves to gamma rays, our galaxy shines in wavelengths we cannot see with human eyes. Each wavelength reveals different structures and phenomena, painting a richer picture of the galaxy than visible light alone could ever show. In radio wavelengths, we see the galaxy's cold hydrogen gas, the raw material for star formation. We see pulsars, the rapidly spinning remnants of dead stars, flashing like cosmic lighthouses. We see synchrotron radiation from electrons spiraling in magnetic fields, tracing out the galaxy's magnetic structure. In the infrared, we see through the dust to the galaxy's core. We see cool stars and brown dwarfs that are too faint to shine brightly in visible light. We see protostellar disks and planets forming around young stars. In visible light, we see the stars themselves, the glowing gas of emission nebulae, and the reflected light from dust clouds. This is the wavelength range our eyes evolved to detect, so it's what the galaxy looks like to us naturally. In ultraviolet, we see the hottest, most massive stars. We see supernova remnants and regions where intense radiation is ionizing the surrounding gas. We see the galaxy's ongoing star formation in brilliant detail. In X-rays, we see the most violent phenomena. Neutron stars and black holes accreting matter from companion stars, heating it to millions of degrees. Supernova remnants expanding into the interstellar medium. Hot gas in the galactic halo. And in gamma rays, the highest energy light, we see cosmic rays interacting with gas, pulsars beaming radiation into space, and perhaps even dark matter annihilation in the galactic center. Each wavelength is a different window on the galaxy, revealing processes and structures invisible in other bands. Together, they paint a complete picture of our cosmic home. Fact 30. Cosmic rays constantly stream through the galaxy. These high-energy particles, mostly protons, race through space at nearly the speed of light. Born in supernova explosions and other violent events, they permeate the Milky Way, passing through planets and bodies as if they were barely there. Silent messengers from distant catastrophes. Every second, billions of cosmic rays pass through your body. Most are low energy and harmless, stopped by Earth's atmosphere, or deflected by the planet's magnetic field. But some are incredibly energetic, carrying as much energy as a baseball thrown at high speed, all concentrated in a single atomic nucleus. These ultra-high energy cosmic rays are rare, but when they strike the upper atmosphere, they create spectacular showers of secondary particles that rain down on the surface. Cosmic rays are accelerated by some of the most violent processes in the universe. Supernova shock waves, the most common source, can accelerate particles to enormous speeds. Pulsars and magnetars, with their intense magnetic fields, can also contribute. Even the galaxy's supermassive black hole, during active periods, may have accelerated cosmic rays. Once accelerated, cosmic rays propagate through the galaxy, bouncing off magnetic field lines and gradually diffusing through space. They don't travel in straight lines. Instead, they follow tangled paths, spiraling around magnetic field lines, which makes it nearly impossible to trace them back to their sources. Cosmic rays play an important role in the galaxy's ecology. They ionize gas in molecular clouds, affecting the chemistry and the rate at which the gas can collapse to form stars. They heat the interstellar medium, and they're a significant component of the energy density in the galaxy, comparable to the energy in starlight, magnetic fields, and turbulent gas motions. They're invisible and intangible to us, but they're an ever-present background radiation filling the galaxy with high-energy particles. Fact 31. The galaxy's magnetic field threads through the disk and halo. Though incredibly weak by earthly standards, this field influences how gas flows, how cosmic rays travel, and how matter organizes itself across vast distances. It's an invisible skeleton that helps shape the galaxy's structure and evolution. Measuring the galactic magnetic field is difficult. It doesn't emit light, and its strength is only a few microgauss, millions of times weaker than a refrigerator magnet. But it can be detected through its effects. Polarized light from distant stars reveals how the magnetic field aligns dust grains. Synchrotron radiation from cosmic ray electrons spiraling in the field emits polarized radio waves. And pulsars, spinning neutron stars with precisely timed pulses, act as cosmic probes whose signals are affected by the magnetic fields they pass through. From these observations, astronomers have pieced together a picture of the galactic magnetic field. It roughly follows the spiral arms, wrapping around the disk in a grand spiral pattern. Near the galactic center, the field becomes more tangled and complex. Above and below the disk, the field extends into the halo, possibly forming loops or bubbles shaped by past outbursts of star formation or activity from the central black hole. The magnetic field affects many galactic processes. It provides pressure support, helping to hold up molecular clouds against gravitational collapse. It shapes the flow of gas in the interstellar medium, channeling it along field lines. It confines cosmic rays, preventing them from escaping the galaxy too quickly. And it may play a role in generating galactic winds, driving gas out of the disk and into the halo or intergalactic space. The magnetic field is a subtle but pervasive influence, quietly shaping the galaxy's behavior in ways that we're still working to fully understand. Fact 32. Supernova explosions enrich the galaxy with heavy elements. When massive stars die in these cataclysmic events, they forge and scatter elements like iron, gold, and uranium into space. These materials mix with gas clouds, eventually forming new stars and planets. Every heavy element in your body was created in such explosions, long ago and far away. Supernovae are among the most powerful events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy, releasing more energy than the sun will emit over its entire 10 billion-year lifetime. The energy comes from gravitational collapse. When a massive star exhausts the nuclear fuel in its core, there's nothing left to support it against gravity. The core collapses in a fraction of a second, releasing an enormous amount of gravitational potential energy. Most of this energy is carried away by neutrinos, but a small fraction, about 1%, is converted into kinetic energy of the explosion. This is enough to blow the star apart at speeds of thousands of kilometers per second. The conditions in a supernova are extreme. Temperatures reach billions of degrees. Densities become so high that nuclei are forced together, building up heavy elements through rapid neutron capture. Elements like gold, platinum, and uranium, which cannot be created in normal stellar fusion, are forged in these few seconds of nuclear chaos. Then, the explosion disperses all this newly created material into space. The ejecta plow into the surrounding interstellar medium, creating a supernova remnant that expands for tens of thousands of years. The shock wave heats and compresses nearby gas clouds, potentially triggering new star formation. And the heavy elements mix into the gas, enriching it for the next generation of stars. Every atom in your body heavier than helium was created in a star. some in the normal fusion processes of stellar cores, but many in supernova explosions. You are made of stardust, quite literally, assembled from the ashes of dead stars that exploded long before the sun and earth existed. Fact 33. There have been supernova in our cosmic neighborhood. The nearest recent supernova visible from Earth occurred centuries ago, their remnants still glowing faintly in our telescopes. These explosions sent shock waves rippling through nearby space, compressing gas clouds and possibly triggering new waves of star formation near our sun. Several historical supernovae were recorded by ancient astronomers. In 1054 CE, Chinese, Japanese, and Arab astronomers documented a guest star in the constellation Taurus that was bright enough to be visible during the day. This was the supernova that created the Crab Nebula, a glowing cloud of gas still visible today, expanding at thousands of kilometers per second. In 1552, Tycho Brahe observed a supernova in Cassiopeia, and in 1604, Johannes Kepler observed another in Ophiuchus. These were the last supernova visible to the naked eye in our galaxy. The most recent nearby supernova was SN 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Though technically not in our galaxy, it was close enough, only about 160,000 light-years away, that it was visible to the naked eye and studied extensively by modern telescopes. Supernova in the Milky Way are relatively rare, occurring perhaps once or twice per century on average. Many are hidden by dust and go unnoticed in visible light, but they can be detected in other wavelengths. The most recent supernova confirmed in our galaxy exploded around 1680, though its light was obscured by dust and was not observed at the time. Its remnant, Cassiopeia A, is now one of the brightest radio sources in the sky. These nearby supernovae have profound effects on the local interstellar medium. They create bubbles of hot gas, accelerate cosmic rays, and disperse heavy elements. Some astronomers have even speculated that a nearby supernova might have triggered the collapse of the gas cloud that formed our solar system 4.6 billion years ago. The evidence is circumstantial, but it's a reminder that we live in a dynamic galaxy where stellar death can influence stellar birth. Fact 34. Pulsars are spinning neutron stars that act as cosmic lighthouses. When massive stars collapse, they sometimes leave behind incredibly dense cores that spin rapidly, beaming radiation into space. These pulsars flash with precise regularity, some rotating hundreds of times per second, serving as natural timekeepers scattered throughout the galaxy. A neutron star is one of the densest objects in the universe. It packs more mass than the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh as much as a mountain on Earth. These objects are so dense that atomic structure breaks down. Electrons are forced into protons, creating neutrons, and the entire star becomes essentially a giant atomic nucleus held together by gravity. When a neutron star forms, it conserves the angular momentum of the original star's core. Just as a figure skater spins faster when pulling in their arms, the collapsing core spins faster as it shrinks. Newly formed neutron stars can rotate hundreds of times per second. They also have incredibly strong magnetic fields, trillions of times stronger than Earth's. As the neutron star rotates, its magnetic field sweeps around, and charged particles accelerated. Near the magnetic poles emit beams of radiation. If these beams happen to point toward Earth, we see a pulse each time the beam sweeps past, like the flash from a lighthouse. The timing of pulsar pulses is extraordinarily stable. Some pulsars keep time more accurately than atomic clocks, making them useful for all sorts of scientific applications. Astronomers use pulsars to test general relativity, to search for gravitational waves, and even to navigate spacecraft. Arrays of pulsars across the galaxy are being used to detect low-frequency gravitational waves from supermassive black hole mergers. These dead stars, spinning silently in the dark, have become some of our most valuable tools for exploring the universe. Fact 35. Binary star systems are common in the Milky Way. Many stars are not solitary like our Sun, but orbit in pairs or even larger groups. These systems can exchange mass, interact gravitationally, and sometimes end their lives in dramatic fashion when one star explodes or collapses into a compact remnant. Surveys suggest that roughly half of all Sun-like stars are in binary or multiple systems. For more massive stars, the fraction is even higher. Binary systems form when a collapsing gas cloud fragments into two or more cores, or when stars in a young cluster become gravitationally bound to each other. The dynamics of binary systems are fascinating. If the two stars are widely separated, they evolve independently, each following its own stellar evolution path. But if they're close together, they can interact. If one star swells into a red giant, it may overflow its Roche lobe, the region of space where its gravity dominates. Material from the giant can flow onto its companion, changing the evolution of both stars. In some cases, this mass transfer can lead to spectacular outcomes. If a white dwarf accretes enough matter from a companion, it can ignite runaway fusion on its surface, creating a nova, a sudden brightening visible from Earth. If the white dwarf's mass grows beyond a critical limit, it can collapse and explode as a Type Ia supernova, one of the brightest types of stellar explosions. Binary systems containing neutron stars or black holes can be even more exotic. As the two compact objects orbit each other, they emit gravitational waves, slowly losing energy and spiraling inward. Eventually, they merge in a violent collision that sends ripples through space-time itself. The detection of these gravitational waves by LIGO and Virgo has opened a new window on the universe, allowing us to observe events that emit no light but shake the very fabric of space. Fact 36. Some binary systems contain black holes or neutron stars. When one member of a binary becomes a compact object, it can pull matter from its companion, creating brilliant X-ray sources. These systems are laboratories for extreme physics, where matter spirals inward at tremendous speeds before vanishing beyond an event horizon. X-ray binaries are among the brightest X-ray sources in the galaxy. A normal star orbits a neutron star or black hole. The compact object's gravity pulls matter from its companion, forming an accretion disk around the compact object. As material in the disk spirals inward, friction heats it to millions of degrees, hot enough to emit copious X-rays. Some X-ray binaries are persistent, shining steadily for years or decades. Others are transient, flaring up suddenly when a chunk of matter falls onto the compact object, then fading again. The behavior depends on the mass transfer rate, the orbital configuration, and the properties of the compact object. These systems allow us to study physics in regimes we cannot reproduce on Earth. Near a black hole, space and time are severely warped. Matter can orbit at a significant fraction of the speed of light. The strong gravitational field causes time dilation and gravitational redshift. The accretion disk can become so hot that iron atoms in the gas fluoresce, emitting characteristic X-ray lines that are smeared and distorted by the extreme conditions. By studying X-ray binaries, astronomers can measure the masses of neutron stars and black holes, test general relativity, and learn about the behavior of matter under extreme conditions. These systems are rare. Only a few hundred are known in the galaxy, but they provide invaluable insights into some of the universe's most exotic objects. Fact 37. The galaxy contains vast bubbles of hot gas. Supernova explosions can create enormous cavities in the interstellar medium, pockets of million-degree gas that glow in X-rays. These bubbles can span hundreds of light years, carved out by the violent deaths of massive stars in stellar nurseries. When massive stars form in clusters, many of them explode as supernova within a relatively short time span, a few million years. Each explosion sends a shock wave into the surrounding gas, sweeping it up and heating it. Multiple supernova in the same region can blow overlapping bubbles that merge into larger structures called superbubbles. These superbubbles are filled with hot, tenuous gas at temperatures of millions of degrees. The pressure of this hot gas is high enough to push against the cooler, denser gas of the interstellar medium, creating an expanding shell. Over time, the superbubble can grow to hundreds of light years in diameter. If it reaches the edge of the galactic disk, it can even break through, venting hot gas into the halo. We live inside one of these structures, called the local bubble. The Sun and nearby stars reside in a region of lower than average gas density, surrounded by a shell of slightly denser gas. This cavity was probably created by supernova explosions a few million years ago. The local bubble is filled with very hot, very thin gas that emits soft X-rays. It extends for hundreds of light years in all directions, a cosmic cavity in which we find ourselves. Superbubbles play an important role in regulating the interstellar medium. They stir the gas, mixing heavy elements created in supernova throughout larger volumes. They can trigger star formation by compressing gas in the surrounding shell, and they drive galactic winds, helping to transport energy and material from the disk into the halo. They're one of the ways the galaxy breathes, cycling material between different phases and different regions. Fact 38. The Fermi bubbles extend above and below the galactic center. These enormous structures stretch tens of thousands of light years into space, glowing in gamma rays. They may be remnants of an ancient outburst from the central black hole, or evidence of intense star formation long ago. Their origin remains mysterious. The Fermi bubbles were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. They're enormous, each lobe extending roughly 25,000 light-years above or below the galactic plane, together encompassing a region larger than the visible galaxy itself. They emit high-energy gamma rays, the most energetic form of light, as well as X-rays and microwave radiation. The edges of the bubbles are surprisingly sharp, suggesting they were created in a relatively sudden event. But what that event was remains unclear. One hypothesis is that a few million years ago, the supermassive black hole at the galaxy's center went through an active phase, consuming a large amount of matter and producing powerful jets of particles and energy. These jets would have inflated the bubbles, filling them with energetic particles that now emit gamma rays as they interact with ambient gas and light. Another possibility is that the bubbles were created by a burst of intense star formation in the galactic center, leading to multiple supernova explosions in a short time span. The combined energy from these explosions could have driven a powerful wind that blew out the bubbles. Whichever explanation is correct, the Fermi bubbles are evidence that the galactic center has not always been as quiet as it appears today. Something dramatic happened there in the relatively recent past, on timescales of millions of years, recent by galactic standards. The bubbles remain as monuments to that event, gigantic structures that reveal the galaxy's dynamic history. Fact 39. The Milky Way's central black hole is currently quiet. Though it contains more than 4 million solar masses, Sagittarius A star is not actively consuming large amounts of material. It appears dormant compared to the brilliant quasars seen in distant galaxies, sleeping at the heart of our cosmic home. This quietness is somewhat unusual. Many galaxies, especially in the distant past, host active galactic nuclei where the central black hole is actively feeding, heating, accreted gas to millions of degrees and producing brilliant emission across the electromagnetic spectrum. Some of these active black holes outshine all the stars in their host galaxies combined, but Sagittarius A star is faint. It emits some radiation as gas trickles onto it, producing occasional flares in X-rays and infrared. But the accretion rate is very low, far below what the black hole could consume if more material were available. The black hole is effectively starving. Why is our galactic center so quiet? Part of the reason is that there simply isn't much gas available in the immediate vicinity. The region within a few light years of the black hole contains stars but relatively little interstellar matter. Without a steady supply of fuel, the black hole cannot sustain vigorous accretion. This quietness is probably temporary on cosmic timescales. If a gas cloud or even a star wanders too close to the black hole, it could be torn apart and accreted, temporarily lighting up the galactic center. In the past, Sagittarius A star may have been much more active, and in the future, especially after the Milky Way merges with Andromeda, it will likely become active again as new material is funneled toward the center. For now, though, we live at a time when the heart of our galaxy is dormant, a sleeping giant rather than a roaring monster. Fact 40. Long ago, the galactic center may have been much more active. Evidence suggests that millions of years ago, the central black hole may have been feeding voraciously, perhaps even shining as a quasar. If so, the Milky Way would have looked dramatically different, its core blazing with light and energy. One piece of evidence for past activity comes from the Fermi bubbles, the giant gamma-ray structures extending above and below the galaxy. Another comes from structures called the Fermi haze, regions of excess microwave and gamma-ray emission near the galactic center. These features suggest that a few million years ago, something energetic happened. If the black hole flared up, it would have produced jets and winds that could inflate these structures. Another intriguing clue comes from observations of gas clouds beyond the galaxy. Some of these clouds show signs of ionization, meaning they've been bathed in intense ultraviolet light. But there's no obvious source for this light in the current galaxy. One explanation is that millions of years ago, the galactic center was much brighter, emitting enough ultraviolet light to ionize gas hundreds of thousands of light years away. We're seeing the afterglow of that event, light that left the galactic center long ago and is only now reaching and ionizing distant clouds. If true, it means that not long ago, astronomically speaking, the Milky Way hosted a mini quasar at its core. The galaxy would have looked very different from the outside, with brilliant emission from the center dominating the overall appearance. From Earth, the sky would have been brighter, with more high-energy radiation reaching the solar system. It's even possible, though speculative, that this activity could have affected life on Earth, perhaps influencing climate or causing extinctions through increased cosmic ray flux. The evidence for past activity is still circumstantial, but it's mounting. The galaxy's center has a history, and that history includes periods of violence we're only beginning to uncover. Fact 41. Gas and dust occasionally fall into the central black hole. Astronomers have watched clouds of material approach Sagittarius A star, torn apart by tidal forces as they near the event horizon. Some material escapes, some is heated to brilliant temperatures, and some crosses a point of no return, vanishing forever into the black hole. One particularly famous event was the approach of a gas cloud called G2. In the early 2010s, astronomers tracked this cloud as it approached the black hole on a close orbit. There was speculation that the cloud would be tidally disrupted and partially accreted, producing a dramatic flare. In the end, G2 passed its closest approach in 2014 without the predicted fireworks. The cloud was stretched and heated, but no major outburst occurred. The event taught astronomers that predicting accretion onto black holes is difficult. Gas doesn't fall in as easily as you might think. The black hole is surrounded by a region of hot, magnetized gas that can resist inflow. Angular momentum has to be shed before gas can spiral inward, and jets and winds driven by the accretion process can actually blow material away. Still, Sagittarius A star does occasionally flare. Infrared and X-ray telescopes have recorded brief brightenings, lasting hours, when the black hole's emission increases by factors of a few to several times. These flares might be caused by clumps of gas or even asteroids falling in, briefly heating the inner accretion flow before vanishing. Each flare gives astronomers a chance to study the region immediately around the event horizon, testing general relativity and learning about how matter behaves in the universe's strongest gravitational fields. The black hole may be quiet most of the time, but it's not completely dormant. It nibbles at the available gas, producing flickers of light that reveal its presence. Fact 42. The galaxy rotates once every few 100 million years at our location. This is the rhythm of our cosmic neighborhood, the slow turning of the disk as it orbits the center. Stars near the core complete their orbits faster, while those in the outer reaches take much longer, creating the galaxy's spiral structure. Near the very center of the galaxy, within the inner few hundred light years, stars orbit the black hole in just a few million years or less. The fastest stars, those within a light year of Sagittarius A star, complete their orbits in just a few years. These stars are moving at significant fractions of the speed of light, their orbits severely affected by general relativity. Out where we are, about 26,000 light-years from the center, the orbital period is around 225 to 250 million years. We've completed about 20 orbits since the solar system formed. Each orbit is a vast journey through the galaxy, carrying us through different regions of the disk, in and out of spiral arms, up and down through the galactic plane. Even farther out, in the sparse outer disk and halo, orbital periods can exceed 1 billion years. Stars there move slowly, taking eons to complete a single circuit. This differential rotation, with inner regions orbiting faster than outer ones, is what winds up the spiral arms and creates the galaxy's dynamic structure. It also creates shear in the disk, stirring the interstellar medium and contributing to the turbulence that regulates star formation. The galaxy is not a rigid body. It's a fluid, dynamic structure where different parts move at different rates, creating a complex dance of matter and motion that has persisted for billions of years. Fact 43. The Milky Way is moving through space. Our galaxy is not stationary. It's falling toward the Virgo cluster, being pulled by the gravity of countless galaxies beyond our local group. Everything in the universe is in motion, from planets to stars to entire galaxies, all drifting through the cosmic web. Our motion is complex, layered, a combination of multiple velocities. The Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the galactic center at about 230 kilometers per second. But the galaxy itself is also moving. Relative to the cosmic microwave background, the ancient light left over from the Big Bang, the Milky Way is moving at about 600 kilometers per second. This motion has several components. We're falling toward the Virgo cluster, a large collection of galaxies about 50 million light-years away. But we're also being pulled toward an even larger structure called the Great Attractor, and beyond that, toward an enormous supercluster called Laniakea. The local group, containing the Milky Way, Andromeda, and their satellites, is moving as a unit through this larger landscape. We're part of the cosmic web, the vast network of galaxy clusters and filaments that fills the universe. The web formed from tiny density fluctuations in the early universe, which grew over billions of years under the influence of gravity. Galaxies formed along the densest filaments and at the nodes where filaments intersect. Now, billions of years later, galaxies still flow along these filaments, pulled by gravity towards the densest regions. The Milky Way is caught up in these flows, drifting through space at hundreds of kilometers per second. But the distances are so vast that even at these speeds, the large-scale structure changes slowly. Over billions of years, the local group will fall into larger structures, eventually merging with other groups and clusters, building ever larger gravitationally bound systems. Fact 44. The Andromeda Galaxy is approaching us. Our nearest large galactic neighbor is moving toward the Milky Way at about 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will collide, merging over eons into a single larger elliptical galaxy. This future merger will reshape both spiral structures entirely. Andromeda, also known as M31, is a slightly larger spiral galaxy about 2.5 million light-years away. It's the most distant object visible to the naked eye, appearing as a faint, fuzzy patch in the constellation Andromeda. Like the Milky Way, it's a barred spiral with a supermassive black hole at its center, a disk full of stars and gas, and a halo of dark matter. For most of the 20th century, astronomers knew Andromeda was approaching us, but they weren't sure whether a collision was inevitable. The problem was measuring Andromeda's motion across the sky, its tangential velocity. If Andromeda had significant sideways motion, it might miss us. But in the early 2000s, precise measurements using the Hubble Space Telescope showed that Andromeda's tangential velocity is small. It's heading almost directly toward us. A collision is unavoidable. The merger will take billions of years. The two galaxies will approach, swing past each other in a first close encounter that will stretch both into long tidal tails. Then, over hundreds of millions of years, they'll fall back together and interpenetrate, their disks overlapping and merging. Stars will almost never collide directly. The distances between them are too vast, but the galaxy's shapes will be completely disrupted. The spiral arms will be destroyed. The disks will be stirred and puffed up. Eventually, after several billion years, the two galaxies will settle into a single large elliptical galaxy, a ball of stars with no disk structure and little gas left for star formation. It will be a quiet, mature system, the final product of this cosmic collision. Fact 45. The collision with Andromeda will be slow and graceful. Despite the name, this galactic collision won't be violent. Stars are so far apart that direct impacts will be rare. Instead, gravity will stretch and warp both galaxies, creating long tidal tails and eventually blending them into a new cosmic structure. It's important to understand the scales involved. Even though galaxies contain hundreds of billions of stars, the stars themselves are tiny compared to the spaces between them. If you shrink the sun down to the size of a grain of sand, the nearest star would still be several kilometers away. A galaxy is mostly empty space, with tiny points of matter scattered through enormous volumes. When two galaxies collide, their stars pass by each other like gnats in two intersecting swarms. The probability of any two stars actually hitting each other is astronomically small. Most stars will simply pass through the other galaxy's disk without coming anywhere near another star. But gravity affects everything, even at a distance. As the two galaxies interpenetrate, the gravitational field becomes chaotic. Stars' orbits are perturbed. Some are flung out into intergalactic space. Others sink toward the center of the merged system. The overall structure is disrupted as the orderly spiral disks are stirred into a more random distribution. Gas clouds in the two galaxies will collide because, unlike stars, gas is extended and can interact over large volumes. These collisions will compress the gas, triggering intense bursts of star formation. The merger will likely produce millions of new stars, lighting up the combined system in a starburst phase. Eventually, though, most of the gas will be consumed or heated and ejected, and star formation will cease. The end result will be an old red elliptical galaxy, beautiful in its own way, but very different from the spirals that created it. Fact 46. The merged galaxy has already been nicknamed Milky Way. Astronomers playfully call the future combined galaxy Milky Way or Milkdromeda. It will likely be a large elliptical galaxy, lacking the spiral arms of its parent galaxies, but containing all their stars, gas, and dark matter mixed together into a new form. Milky Way will be one of the largest galaxies in the local group, containing perhaps 1 trillion stars. It will have a massive dark matter halo and a central supermassive black hole formed from the merger of the Milky Way's and Andromeda's black holes. This new black hole will contain over 100 million solar masses, far more massive than either parent black hole. The process of black hole merging is itself fascinating. As the two galaxies merge, their central black holes will sink towards the center of the combined system through a process called dynamical friction. they lose energy by gravitationally interacting with nearby stars, which get flung away, carrying off angular momentum. Eventually, the two black holes will form a binary, orbiting each other at ever-decreasing distances. When they get close enough, they'll begin emitting strong gravitational waves, losing energy and spiraling together faster and faster. In the final moments, they'll merge in a violent event that sends ripples through space-time, briefly emitting more power and gravitational waves than all the stars in the observable universe combined. The merged black hole will then ring down, settling into a new, larger black hole at the center of Milky Way. All of this is still billions of years in the future. By the time Milky Way forms, the Sun will have long since left the main sequence. It will be swelling into a red giant right around the time the galaxies first collide. Earth may be uninhabitable or even destroyed by the Sun's expansion. Whatever intelligent life exists at that time, if any, will witness a spectacular show in the sky as the two galaxies dance and merge overhead. Fact 47. Our solar system will likely survive the merger, though the galaxy will be dramatically reshaped. The vast distances between stars mean our sun and planets will probably pass through unscathed. The night sky will look spectacular as the two galaxies interpenetrate, but Earth itself should remain safe in its orbit. The probability of our sun colliding with another star during the merger is incredibly tiny, less than 1 in a billion. Space is just too empty for collisions to be common. What's more likely is that our sun's orbit will be perturbed. Instead of continuing its orderly circular path around the galactic center, the sun might be kicked into a more elliptical orbit, perhaps moving farther out into the merged system or even into the halo. But this will happen gradually, over millions of years, and won't directly affect the planets. The night sky, on the other hand, will be transformed. As Andromeda approaches, it will grow larger and larger in the sky, eventually stretching across tens of degrees. During the first close passage, tidal forces will pull long streamers of stars from both galaxies, creating arcs and bridges of light across the heavens. When the disks interpenetrate, the combined starlight will be spectacular, with bright knots of star formation lighting up like cosmic fireworks. The view from Earth, if anyone is around to see it and if Earth is still habitable, will be unlike anything we can observe today. It will be a reminder that even galaxies are not permanent. They too are born, evolve, and eventually merge or die, part of the ongoing transformation of the universe. Fact 48. The Milky Way belongs to the local group. This collection of more than 50 galaxies includes the Milky Way, Andromeda, and many smaller dwarf galaxies. Together, they form a gravitationally bound cluster spanning millions of light years, a small cosmic family drifting through the universe. The local group is a modest galaxy group as these structures go. It's dominated by two large spirals, the Milky Way and Andromeda, with a smaller spiral, Triangulum, as a distant third. The rest are dwarf galaxies, ranging from relatively bright systems like the large and small Magellanic Clouds to ultra-faint dwarfs with only a few thousand stars, barely more luminous than a single massive star. The local group occupies a region about 10 million light-years across. Within this volume, all the galaxies are gravitationally bound to each other. They orbit within the group, occasionally merging or being disrupted by close encounters. Beyond the local group, The nearest significant galaxy groups are millions of light-years away, separated by vast voids of near-empty space. The local group is part of the larger cosmic web, sitting on a filament that connects to the Virgo cluster and beyond. Over time, the local group will evolve. Small, dwarf galaxies will continue to be absorbed by the Milky Way and Andromeda. The Milky Way and Andromeda will merge. Triangulum may also be absorbed in the distant future. Eventually, the local group will likely be reduced to a single giant elliptical galaxy, the end product of billions of years of mergers and interactions. But that fate is still billions of years away. For now, the local group is a dynamic collection of galaxies, a neighborhood in which we can study galactic interactions and evolution up close. Fact 49. Most galaxies in the local group are dwarfs. The Milky Way and Andromeda dominate by mass and size, but most of the group's members are small, faint galaxies. Some contain only a few million stars and are so dim they're barely visible even with powerful telescopes. They orbit the larger galaxies like satellites. These dwarf galaxies come in several types. Dwarf, irregular galaxies have chaotic structures with ongoing star formation. Dwarf, elliptical galaxies are smooth and featureless, containing mostly old stars. Dwarf, spheroidal galaxies are extremely faint and diffuse, often dominated by dark matter with very few stars. Some dwarf galaxies are so faint they were discovered only recently in surveys like the Sloan Digital Sky Survey, and later with data from the Gaia spacecraft. These ultra-faint dwarfs challenge our understanding of galaxy formation. They contain so little luminous matter that they're essentially dark matter halos with a handful of stars. Why star formation was so inefficient in these systems is still being investigated. Dwarf galaxies are important for understanding the universe's structure and evolution. According to cosmological models, large galaxies like the Milky Way formed hierarchically from the mergers of many smaller systems. Dwarf galaxies are the building blocks, and the ones we see today are the survivors that haven't yet been absorbed. By studying them, astronomers can test models of galaxy formation and learn about the nature of dark matter. They also serve as probes of the early universe. Because they're small and have weak gravity, dwarf galaxies are easily affected by their environment. Studying how they interact with larger galaxies, how they lose their gas and stop forming stars, helps us understand the processes that shape galaxies across cosmic time. Fact 50. The large and small Magellanic Clouds are satellite galaxies. Visible from the southern hemisphere, these irregular dwarf galaxies orbit the Milky Way. Recent evidence suggests they may be on their first close passage rather than being long-term companions. Their interaction with our galaxy has created streams of gas trailing behind them. The Magellanic Clouds are among the most prominent objects in the southern night sky. They look like detached pieces of the Milky Way, glowing patches of stars visible to the naked eye. They've been known to humans since prehistory, and European explorers in the Age of Discovery brought knowledge of them back to the northern hemisphere. The large Magellanic Cloud is about 160,000 light-years away and contains roughly 30 billion stars. The small Magellanic Cloud is about 200,000 light-years away with about 3 billion stars. Both are irregular galaxies, lacking the spiral or elliptical structure of larger systems. They're rich in gas and actively forming stars. For a long time, astronomers assumed the Magellanic Clouds were long-term satellites of the Milky Way, orbiting for billions of years. but improved measurements of their velocities suggest they're moving quite fast, faster than expected for bound satellites. It's now thought they might be on their first close pass around the Milky Way, having fallen in from the broader local group. If so, they're newcomers, rather than long-term companions. Their passage near the Milky Way has had consequences. Tidal forces have pulled gas from the Magellanic Clouds, creating the Magellanic Stream, an enormous ribbon of hydrogen gas that wraps around the southern sky. This gas will eventually fall back into the Milky Way, fueling future star formation. The clouds themselves may eventually be torn apart and absorbed, adding their stars to the Milky Way's halo, though this won't happen for 1 billion years or more. Fact 51. The Magellanic Stream is a river of hydrogen gas. Stretching across the southern sky, this enormous stream was pulled from the Magellanic Clouds by tidal forces. It may eventually fall into the Milky Way, providing fresh material for future star formation and adding to our galaxy's mass over time. The Magellanic Stream is one of the largest structures in the local group. It extends over 200 degrees across the sky, encompassing a huge volume of space. It contains hundreds of millions of solar masses of gas, though spread so thinly that it's invisible to the eye and was only discovered through radio observations of neutral hydrogen. The stream has a complex structure. In addition to the main stream trailing behind the Magellanic Cloud's motion, there's a leading arm ahead of them. There are also branches and filaments suggesting a complicated interaction history. The exact origin of the stream is still debated. It was probably created by a combination of tidal forces from the Milky Way pulling gas out of the clouds and interactions between the large and small Magellanic Clouds themselves as they orbit each other. The Magellanic Stream is evidence that the Milky Way is still actively accreting material. The gas in the stream is gradually falling back toward the galactic disk. Over the next 1 billion years or so, it will rain down onto the disk, providing raw material for new generations of stars. This infall helps explain how the Milky Way continues to form stars despite having depleted much of its original gas supply. Accretion from satellite galaxies and streams like this replenishes the reservoir. The stream is also a useful probe of the Milky Way's halo. The motions of the gas reveal the gravitational field it's moving through, allowing astronomers to map the distribution of dark matter in the halo. These studies have provided some of the best constraints on the Milky Way's total mass and the extent of its dark matter halo. Fact 52. Dozens of dwarf galaxies orbit the Milky Way. These small companions are scattered in a rough spherical distribution around our galaxy. Many have been discovered only recently as surveys become more sensitive. They're important for understanding how galaxies form and how dark matter is distributed in the universe. The Milky Way's known satellite galaxies number over 50, and the total population is likely much higher. Many of these satellites are incredibly faint, discovered only in the last 2 decades through careful searches of survey data. They have names like Segway 1, Butas Y, and Tucana Descent, often named after the constellations in which they appear. Some of these ultra-faint dwarfs contain fewer than 1,000 stars and are among the smallest, dimmest galaxies known. They're so faint that if they were moved to the distance of Andromeda, they would be invisible even with our best telescopes. Yet they're galaxies, light-bound systems of stars orbiting within a dark matter halo. The spatial distribution of these satellites has provided puzzles for cosmologists. Simulations of dark matter predict that large galaxies should be surrounded by thousands of small dark matter halos, but we see only dozens of satellite galaxies. This is called the missing satellites problem. Possible solutions include the idea that star formation is inefficient in small halos, leaving many halos dark, or that feedback from the first stars prevented gas from cooling and forming stars in the smallest halos. Satellite galaxies are also important for understanding the hierarchical formation of galaxies. According to theory, the Milky Way grew by accreting these smaller systems. The satellites we see today are the ones that survived. Many others have already been absorbed. By studying the current population, we can constrain models of how galaxy formation proceeded over cosmic time. Fact 53. Some dwarf galaxies are dominated by dark matter. Certain ultra-faint dwarfs contain so little visible matter that they're held together almost entirely by dark matter. They're among the most dark matter-rich objects known, making them valuable laboratories for studying this mysterious invisible substance. The most extreme examples have mass-to-light ratios of several hundred to 1,000 or more. That means for every solar mass of stars, there are hundreds or thousands of solar masses of dark matter. These galaxies are essentially dark matter halos that happen to have a few stars in them, rather than stellar systems with some dark matter mixed in. These dark matter-dominated dwarfs are prime targets for dark matter searches. Some theories predict that dark matter particles can annihilate or decay, producing gamma rays. If this happens, the densest regions of dark matter, like the centers of dwarf galaxies, should emit gamma rays. By observing these dwarfs with gamma-ray telescopes and looking for excess emission, astronomers hope to detect dark matter directly. So far, no confirmed detections have been made, but the searches continue. These ultra-faint dwarfs also help constrain the properties of dark matter itself. Their structure depends on what kind of particle dark matter is. If dark matter is cold, meaning the particles move slowly, halos can be small and dense. If dark matter is warm, with faster-moving particles, small halos are suppressed. By measuring the properties of the smallest galaxies, astronomers can rule out certain dark matter models and narrow down the possibilities. In a sense, these tiny, faint galaxies are windows into the universe's invisible scaffolding. They reveal the dark matter structure that underlies all cosmic structure, giving us hints about the nature of the dominant component of the universe's mass. Fact 54. The galaxy has a thick disk and a thin disk. These two components have different populations of stars. The thin disk contains younger stars, gas, and active star formation. The thick disk holds older stars on more elliptical orbits. Together, they create the layered structure of the Milky Way's stellar disk. The thin disk is where most of the action happens. It's only about 1,000 light-years thick and contains the majority of the galaxy's gas. Star formation is concentrated here, particularly in the spiral arms. The stars in the thin disk are relatively young and metal-rich, products of recent stellar generations. They orbit in nearly circular paths close to the galactic plane. The thick disk extend farther above and below the plane, perhaps 3,000 light-years or more. Its stars are older, typically 8 to 10 billion years old, and have lower metallicities, indicating they formed earlier in the galaxy's history. Their orbits are more elliptical and more inclined to the plane, giving the thick disk its puffed-up structure. The thick disk may have formed in several ways. One possibility is that it's the heated remnant of an earlier thin disk, puffed up by ancient mergers like the Gaia and Enceladus collision 10 billion years ago. Another possibility is that it formed directly from turbulent gas in the early galaxy before the thin disk fully settled. It might also contain stars that migrated from the inner galaxy over time. Distinguishing between these scenarios is an active area of research. The boundary between the thin and thick disks is not sharp. Stars span a continuum of ages, metallicities, and orbital properties, but statistically, the two components are distinct, revealing that the galactic disk has a layered structure that reflects its complex formation history. Fact 55. Stellar populations reveal the galaxy's history. By studying the ages and compositions of different star groups, astronomers can reconstruct how the Milky Way formed and evolved. Older, metal-poor stars in the halo tell of early times, while younger metal-rich stars in the disk reveal more recent history. The concept of stellar populations was developed in the mid-20th century. Astronomers realized that stars could be grouped into two main populations based on their properties. Population 1 stars are young, metal-rich, and found in the disk. Population 2 stars are old, metal-poor, and found in the halo and globular clusters. These populations reflect different eras of the galaxy's history. Population 2 stars formed early, when the universe was still relatively metal-poor. Population I stars formed later, from gas enriched by previous generations. By measuring stellar ages and metallicities in detail, astronomers can go further, tracing out the star formation history of different parts of the galaxy. For example, studies of stars in the solar neighborhood show that star formation has been relatively continuous over the last 10 billion years, with some periods of enhanced activity corresponding to mergers or interactions with satellite galaxies. The thick disk shows a burst of star formation around 10 billion years ago, likely associated with the Gaia-Enceladus merger. The inner bulge shows evidence of very early, rapid star formation, producing a population of old, metal-rich stars. Each stellar population is like a layer in the galaxy's archaeological record, preserving information about the conditions when those stars formed. By reading this record, astronomers piece together the Milky Way's biography, a story of gradual growth punctuated by dramatic mergers and ongoing star formation. Fact 56. Open star clusters are stellar nurseries that gradually disperse. Unlike ancient globular clusters, open clusters are younger and loosely bound. They form in molecular clouds, shine brightly for millions of years, then slowly scatter as their stars drift apart. The Pleiades is a famous example visible to the naked eye. Open clusters contain dozens to thousands of stars born together from the same gas cloud. They're loosely gravitationally bound, and their stars have similar ages and compositions. The Pleiades, also known as the Seven Sisters, is one of the nearest and most easily observed open clusters, about 440 light-years away and 100 million years old. Other well-known open clusters include the Hyades, the double cluster in Perseus, and the Beehive cluster. Open clusters don't last forever. Over time, gravitational interactions within the cluster and tidal forces from the galaxy gradually pull them apart. low-mass stars evaporate away, wandering off into the general field population. The cluster becomes more and more diffuse until it's no longer recognizable as a cluster at all, typically within a few 100 million years. The Milky Way contains thousands of known open clusters, and probably many more hidden by dust or too old and dispersed to be easily recognized. They're valuable for studying stellar evolution because all the stars in a cluster have the same age but different masses. By observing clusters of different ages, astronomers can see how stars of different masses evolve, testing theoretical models of stellar structure and evolution. Open clusters also serve as tracers of the disk's structure. Their positions and motions help map the spiral arms and reveal how gas and stars flow through the galactic disk. They're signposts of recent star formation, marking where molecular clouds have recently collapsed to form new generations of stars. Fact 57. The Sun likely formed in an open cluster. About 4.5 billion years ago, our star was born alongside hundreds or thousands of siblings. Over time, that cluster dissolved, and the Sun's brothers and sisters scattered across the galaxy. Some may still orbit nearby, but identifying them is difficult. Evidence for the Sun's cluster birth comes from several sources. First, most stars form in clusters, so it's statistically likely the Sun did too. Second, the presence of short-lived radioactive isotopes in meteorites suggests that a nearby supernova enriched the gas cloud that formed the solar system. Such supernovae are most common in massive star-forming regions, which produce clusters. Third, simulations show that clusters with properties similar to what we infer for the Sun's birth cluster are common and disperse on timescales that match the solar system's age. The Sun's birth cluster probably contained a few thousand stars and dispersed over a few 100 million years. By now, those stars have spread out across a large region of the galaxy. Some may have migrated inward or outward, changing their orbital distances from the galactic center. Others may have been kicked out of the disk into the thick disk or halo. Finding the Sun's siblings would be fascinating. They formed from the same gas cloud, so they should have very similar chemical compositions. They should also have similar ages. But the challenge is that 4.5 billion years is a long time. The stars have had many opportunities to encounter other stars, and their orbits have been perturbed. By now, they're scattered over a large volume, and there's no easy way to identify them among the millions of nearby stars. Still, searches are underway. Large surveys measure the motions and compositions of millions of stars, and sophisticated algorithms search for patterns that might indicate shared origins. A few candidate solar siblings have been identified, stars with similar properties to the Sun, but confirming they actually formed together remains difficult. Fact 58. Researchers are searching for the Sun's lost siblings. By analyzing stellar motions and chemical compositions, astronomers hope to identify stars that formed from the same gas cloud as our Sun. Finding these relatives would tell us about the conditions in which the solar system was born. One candidate solar sibling was identified in 2014, a star called HD 162826. Located about 110 light-years away. It has a very similar chemical composition to the Sun and appears to be the same age. Its orbit through the galaxy is also consistent with it having formed in the same region as the Sun. However, proving definitively that two stars are siblings is challenging. They should have identical elemental abundances, since they formed from the same gas. But stars can also be polluted by material accreted from planets or companions, complicating the analysis. They should have formed at the same time, but stellar ages are difficult to determine precisely. And their orbits should be traceable back to a common origin. But uncertainties in the galactic gravitational field and in past encounters with other stars make this difficult. Despite these challenges, the search continues. The Gaia spacecraft has provided precise positions and motions for over 1 billion stars, allowing researchers to trace stellar orbits backward in time. Chemical abundance surveys measure the detailed compositions of hundreds of thousands of stars. Machine learning algorithms sift through this data, looking for patterns. If we can identify a significant number of the Sun's siblings, it would provide a valuable snapshot of the stellar environment in which the solar system formed. Were there many massive stars nearby that could have influenced the formation of the planetary disk? How long did the cluster survive before dispersing? How far have the sibling stars migrated? These questions can only be answered by finding the Sun's long-lost family. Fact 59. The galaxy recycles matter continuously. Stars form from gas, live for millions or billions of years, then return their material to space through stellar winds or explosions. This enriched gas joins the interstellar medium, where it cools and eventually collapses to form new stars. The cycle continues across cosmic time. This cosmic recycling is fundamental to the galaxy's evolution. In the beginning, the gas was nearly pure hydrogen and helium. The first stars fused these light elements into heavier ones like carbon, oxygen, and iron. When these stars died, they ejected their newly created elements into space. The next generation of stars formed from slightly enriched gas, incorporating these heavier elements. Over billions of years, generation after generation, the interstellar medium has been progressively enriched with heavy elements. The Sun, formed 4.6 billion years ago, contains about 2% heavy elements by mass, reflecting the enrichment that had occurred by that time. Stars forming today have even higher metallicities. This enrichment has profound consequences. Heavy elements affect how gas cools and how stars form. They provide the raw materials for planets, allowing rocky worlds like Earth to exist. And they enable complex chemistry, including the organic molecules necessary for life as we know it. The recycling timescale varies. Massive stars live only a few million years before exploding, quickly returning their material to space. Low-mass stars like the Sun live billions of years, locking up their material for much longer. The most massive stars produce more heavy elements, but are rarer. The least massive stars are common, but contribute little to enrichment. The overall rate of enrichment depends on the balance of these factors. In the early universe, enrichment was rapid as the first massive stars formed and died. Now, with fewer massive stars forming and much of the gas already enriched, the process has slowed. But it continues, gradually building up the galaxy's inventory of heavy elements. Fact 60. Every atom in your body has been through multiple stars. The hydrogen in water molecules may be primordial, but heavier elements like carbon, nitrogen, and oxygen were forged in stellar cores and scattered by supernova. We are quite literally made of stardust, assembled from material recycled through the galaxy's long history. Consider a carbon atom in your body. It was created billions of years ago inside a star through the triple alpha process, where 3 helium nuclei fused together. When that star died, perhaps as a planetary nebula or supernova, the carbon was ejected into space. It drifted through the interstellar medium, perhaps becoming part of a molecular cloud. That cloud collapsed to form a new generation of stars, and the carbon atom was incorporated into one of them or into the disk of gas and dust around a young star. Eventually, it became part of a planet, perhaps locked in rocks or ice. Through geological or atmospheric processes, it moved through different reservoirs. Maybe it was part of carbon dioxide in an atmosphere, dissolved in an ocean, incorporated into a mineral, or taken up by a living organism. After billions of years of cycling through stars, clouds, planets, and potentially other life forms, that carbon atom is now part of you. The same is true for every atom in your body except hydrogen. Iron in your blood, calcium in your bones, oxygen in your lungs, all were created in stars. Some were forged in the cores of massive stars and blasted out in supernova. Others were created in collisions between neutron stars. Still others were formed in the winds of dying red giants. The universe is about 13.8 billion years old. The Sun is 4.6 billion years old. That leaves 9 billion years, during which the material that formed the solar system was cycling through the galaxy, being processed by multiple generations of stars, gradually accumulating the heavy elements that now make up the Earth and everything on it, including you. Fact 61. The interstellar medium fills the space between stars. This thin mixture of gas, dust, and plasma seems nearly empty, but contains all the raw material for future star systems. It's stirred by stellar winds, heated by radiation, and compressed by shock waves, creating a dynamic environment that shapes galactic evolution. The interstellar medium is far from uniform. It exists in multiple phases with vastly different properties. Cold molecular clouds are dense and dark, shielding their interiors from stellar radiation. Neutral atomic hydrogen clouds are less dense and more diffuse. Warm, ionized regions surround hot stars, heated to tens of thousands of degrees by ultraviolet light. Hot ionized gas fills superbubbles and extends into the halo, heated to millions of degrees by supernova shocks. Each phase has different physics governing its behavior. Cold clouds can collapse under gravity to form stars. Warm gas can cool and condense, feeding molecular clouds. Hot gas can cool and rain back onto the disk, or it can be driven out of the galaxy entirely by powerful winds. These phases constantly cycle into one another. A supernova explosion heats surrounding gas from warm to hot, creating a bubble. The bubble expands and cools, eventually reaching temperatures where it can condense. The dense shell around the bubble fragments and collapses, forming new stars. Those stars live and die, heating the gas again. The cycle continues. The interstellar medium is also where the galaxy's magnetic field resides. The field helps support clouds against collapse, channels the flow of gas and cosmic rays, and plays a role in generating turbulence that stirs the gas. All these processes, gravity, pressure, magnetic fields, radiation, and turbulence, interact in complex ways to regulate how and where stars form, how the galaxy evolves, and how matter flows through the system over billions of years. Fact 62. Molecular clouds are the coldest places in the galaxy. Within these vast clouds, temperatures can drop to just a few degrees above absolute zero. Shielded from starlight by thick dust, These cold regions are where the densest gas accumulates and begins the slow collapse that leads to star formation. At temperatures of 10 to 20 Kelvin, only a few degrees above the coldest temperature possible, molecular clouds are frigid environments. At these temperatures, hydrogen atoms pair up to form molecular hydrogen, the most abundant molecule in the universe. Other molecules form as well, facilitated by reactions on the surfaces of dust grains. Water ice coats the grains. Carbon monoxide, ammonia, methanol, and hundreds of more complex organic molecules have been detected in dense clouds. The coldness is essential for star formation. Gas can only collapse under its own gravity if it can shed energy by radiating it away. If gas is too hot, thermal pressure prevents collapse. By cooling to such low temperatures, molecular clouds minimize the pressure, support, and allow gravity to take over. The densest cores within molecular clouds, called pre-stellar cores, are on the verge of collapse, poised to form stars. These clouds are also dark. The dust is so thick that visible light cannot penetrate more than a small fraction of a light year into the cloud. Inside the densest regions, it's darker than the darkest night on Earth, with no starlight reaching the interior. Only infrared and radio wavelengths can probe these hidden realms, revealing the cold gas and dust that will soon become stars and planets. The life cycle of molecular clouds is relatively short by galactic standards. Once stars begin forming, the massive ones produce intense radiation and winds that heat and disrupt the cloud. Within a few million years, the cloud is dispersed, its gas either incorporated into stars or blown away into the warmer interstellar medium. The remnants mix with other gas, cool over time, and may eventually participate in forming new clouds, continuing the cycle. Fact 63. Some clouds are massive enough to form thousands of stars. Giant molecular cloud complexes contain enough material to create entire star clusters. Over millions of years, these clouds fragment into smaller clumps, each collapsing to form a star or stellar system, transforming dark clouds into brilliant nebulae. The largest molecular clouds in the galaxy contain millions of solar masses of gas spread over hundreds of light years. These giant complexes are the galaxy's most productive star factories. Within them, hundreds or thousands of dense cores collapse simultaneously, creating entire generations of stars in a single event. The Orion Molecular Cloud Complex is a nearby example. It contains several distinct clouds, including the Orion Nebula region where active star formation is visible, and darker regions like the Horsehead Nebula, where collapse is still in its early stages. The entire complex contains enough material to form tens of thousands of stars for the next few million years. Star formation in these clouds is hierarchical. The cloud as a whole is supported by turbulence, magnetic fields, and thermal pressure. But within it, density fluctuations create regions where gravity overwhelms the support. These regions collapse, fragmenting further as they do so. The result is a nested structure, with larger collapsing regions containing smaller ones, down to individual stellar cores. The most massive clumps form the most massive stars, which are rare but luminous. These massive stars dominate the appearance of the resulting star-forming region, their intense ultraviolet light ionizing the surrounding gas and making it glow in vivid reds and greens. Smaller clumps form lower-mass stars like the Sun, which are far more common but less conspicuous. The combination creates the spectacular emission nebulae we see in photographs. clouds of glowing gas studded with brilliant new stars, monuments to the ongoing process of stellar birth. Fact 64. Stellar winds and radiation sculpt beautiful nebulae. Young, massive stars emit powerful, ultraviolet light that ionizes surrounding gas, making it glow in vivid colors. Stellar winds push material outward, carving pillars and shells. The result is the stunning emission nebulae we see in photographs, cosmic art painted by stellar energy. The Eagle Nebula, with its famous pillars of creation, is a perfect example. Massive stars just outside the pillars emit intense ultraviolet radiation that heats and ionizes the surrounding gas. This radiation also photoevaporates the pillars, gradually eroding them from the outside. But the pillars contain dense knots of gas that are more resistant to erosion. These knots cast shadows, protecting the gas behind them and creating the distinctive pillar shapes. Inside the pillars, new stars are forming, cocooned within the dense gas. Eventually, the radiation will erode the pillars entirely, exposing the young stars within. But for now, the pillars stand as dramatic evidence of the interplay between star formation and stellar feedback. The colors in nebula photographs are not arbitrary. Different elements emit light at specific wavelengths when ionized. Hydrogen glows red at 656 nanometers, the famous H-alpha line. Oxygen glows green at 500 nanometers and red at 630 nanometers, depending on ionization state. Sulfur glows red at 672 nanometers. Nitrogen contributes to red emission. By observing at these specific wavelengths and combining them into color images, astronomers create the spectacular pictures of nebulae that have become iconic. These images are scientifically accurate representations of the light the nebulae emit, though often the colors are adjusted to make details visible or to fit the limitations of human color perception. The structures in nebulae, pillars, shells, arcs, and bubbles reveal the history of interactions between stars and gas. Each shape tells a story of stellar winds pushing outward, radiation carving cavities, supernova shockwaves compressing gas, or binary stars creating spiral patterns. Reading these structures is like reading the history of the region written in light and matter. Fact 65. Planetary nebulae mark the death of sun-like stars. When medium-mass stars exhaust their fuel, they shed their outer layers in glowing shells of gas. The exposed core, a white dwarf, illuminates these expanding clouds, creating intricate structures that fade over thousands of years. They have nothing to do with planets despite their name. The name planetary nebula is a historical accident. Through early telescopes, these objects appeared as small, round, glowing disks, somewhat resembling planets like Uranus or Neptune. But they're actually the ejected outer envelopes of dying stars, shell of gas expanding at tens of kilometers per second, glowing in the light of the hot stellar core at their centers. When a sun-like star exhausts the hydrogen in its core, it swells into a red giant, growing hundreds of times larger than before. The star becomes unstable, pulsating and shedding its outer layers in a series of pulses. Over a few tens of thousands of years, the envelope is completely ejected, revealing the hot core, a white dwarf with surface temperatures of 100,000 degrees or more. This white dwarf emits intense ultraviolet radiation that ionizes the expanding shell, making it glow. The result is a planetary nebula, a beautiful bubble of light expanding into space. The shapes of planetary nebulae are astonishingly diverse. Some are simple spheres. Others are bipolar, with two lobes extending in opposite directions. Still others have multiple shells, rings, or complex filamentary structures. The shapes are thought to result from binary companions, stellar rotation, magnetic fields, or variations in how the mass was lost. Planetary nebulae are short-lived by astronomical standards. They fade over 10 to 20,000 years as the gas disperses and the white dwarf cools, eventually becoming too faint to ionize the nebula. But during their brief existence, they return chemically enriched gas to the interstellar medium, contributing to the cycle of matter that fuels future generations of stars. Fact 66. White dwarfs are the fate of most stars. When stars like our Sun die, they leave behind dense Earth-sized cores composed of carbon and oxygen. These white dwarfs slowly cool over billions of years, gradually fading from white to red to black, becoming stellar embers drifting through the galaxy. A white dwarf is supported not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect. Electrons resist being squeezed too close together, and this resistance can support the star against gravitational collapse, but only up to a limit. If the white dwarf's mass exceeds about 1.4 solar masses, the so-called Chandrasekhar limit, even electron degeneracy pressure cannot hold it up, and it will collapse further. Most white dwarfs are well below this limit, with masses around 0.6 solar masses, packed into a volume about the size of Earth. The density is extreme. A teaspoon of white dwarf material would weigh several tons. Despite being incredibly hot when first exposed, with surface temperatures over 100,000 Kelvin, white dwarfs have no energy source. They shine purely by radiating away their stored thermal energy. Over billions of years, they cool, fading through white, yellow, orange, red, and eventually becoming black dwarfs, cold, dark objects that emit no light. However, the universe is only 13.8 billion years old, and cooling to black dwarf temperatures takes tens of billions of years or more. No black dwarfs exist yet. Every white dwarf in the galaxy is still glowing, though the oldest and coolest are dim and red, difficult to detect. White dwarfs are important as cosmic clocks. By measuring the temperatures of the coolest white dwarfs in a region, astronomers can estimate the age of the stellar population. The coolest white dwarfs must have been formed longest ago, providing a minimum age for the galaxy or star cluster. White dwarfs also play a role in type Ia supernova. If a white dwarf in a binary system accretes enough matter from its companion to exceed the Chandrasekhar limit, it can collapse and explode, creating one of the most luminous types of supernova. These explosions are so bright and so consistent in luminosity that they're used as standard candles to measure cosmic distances. Fact 67. The Milky Way contains billions of white dwarfs. Most stars in the galaxy's history were not massive enough to explode as supernova. Instead, they ended as white dwarfs. Many of these ancient remnants populate the galactic halo and disk, cooling slowly, some nearly as old as the galaxy itself. White dwarfs are the most common type of stellar remnant. Over the Milky Way's 13.6 billion-year history, countless stars have lived and died, and the vast majority became white dwarfs. They're everywhere, scattered throughout the disk and halo, silent witnesses to billions of years of stellar evolution. Finding white dwarfs is challenging because they're faint. They emit no new energy, only gradually radiating away heat. The older they are, the cooler and dimmer they become. The faintest white dwarfs are among the hardest objects to detect in the galaxy. Surveys like the Sloan Digital Sky Survey and Gaia have cataloged hundreds of thousands of white dwarfs, revealing their distributions and properties. These surveys show that white dwarfs come in several types, depending on which elements are visible in their spectra. DA white dwarfs show only hydrogen lines. Their surface is covered by a thin hydrogen atmosphere. DB white dwarfs show helium. Others show traces of carbon or heavier elements revealed as the star cools and the thin outer layers mix with the core. The oldest white dwarfs in the galaxy provide constraints on the galaxy's age. They're incredibly old, having cooled for over 12 billion years. By studying the coolest white dwarfs in the halo, astronomers can measure how long it's been since those stars formed, providing independent confirmation of the galaxy's age derived from other methods. The galaxy's population of white dwarfs is a vast graveyard of stars, each one a former sun that once shone brightly, but now fades slowly into darkness, carrying within it the memory of a stellar life that spanned millions or billions of years. Fact 68. Neutron stars are incredibly dense stellar remnants. When massive stars explode, they can leave behind cores compressed to incredible densities. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars represent a state of matter found nowhere else in the accessible universe. The density is so extreme that atomic structure ceases to exist. Protons and electrons are crushed together to form neutrons, and the entire star becomes essentially a single, gigantic atomic nucleus. The physics governing neutron stars is exotic and not fully understood, operating in regimes where quantum mechanics, general relativity, and nuclear physics all become important simultaneously. The surface gravity on a neutron star is about 100 billion times stronger than Earth's gravity. Objects would fall at accelerations that would carry them to relativistic speeds almost instantly. The escape velocity is a significant fraction of the speed of light. Space-time around a neutron star is severely warped. Light is bent and gravitationally redshifted. Time runs slower near the surface than far away. Neutron stars also have extremely powerful magnetic fields, typically a trillion times stronger than Earth's field. The strongest known magnetic fields in the universe are found in a special class of neutron stars called magnetars, where the field strength approaches the limits of what physics allows. These fields are so strong, they distort the star's shape and affect the behavior of empty space itself. Despite their small size, neutron stars can spin incredibly fast. Pulsars can rotate hundreds of times per second, and the centrifugal forces are so strong that the star bulges at the equator. The rotation is amazingly stable, more precise than atomic clocks, making pulsars natural timekeepers that can be used for navigation and for detecting gravitational waves. Neutron stars are laboratories for extreme physics, allowing scientists to test theories in conditions that cannot be replicated in any earthly laboratory. They probe the limits of density, magnetic field strength, rotation speed, and gravitational field, teaching us about the fundamental properties of matter and space-time. Fact 69. Some neutron stars spin hundreds of times per second. These millisecond pulsars rotate so fast, they complete revolutions in just a few thousandths of a second. They're among the most precise natural clocks in the universe. their rotation rates stable over long periods, useful for detecting gravitational waves and testing physics. Millisecond pulsars are thought to be old neutron stars that have been spun up by accreting matter from a companion star. In a binary system, matter flows from the companion onto the neutron star, forming an accretion disk. As the matter spirals inward, it carries angular momentum, gradually spinning up the neutron star. Over millions of years, the neutron star's rotation can increase from a few rotations per second to hundreds. The fastest known pulsar, PSR J1748-2446ID, rotates 716 times per second. At this speed, the surface near the equator is moving at about 25% of the speed of light. The centrifugal forces are enormous, and the star is only marginally stable. If it spun much faster, it would tear itself apart. The rotation rate would exceed the speed at which material could orbit just above the surface, and the star would fly apart. The stability of millisecond pulsar rotation rates makes them incredibly useful. Arrays of millisecond pulsars scattered across the galaxy are being monitored as part of pulsar timing arrays, projects designed to detect low-frequency gravitational waves. By precisely measuring the arrival times of pulses from many pulsars, astronomers can detect tiny variations caused by gravitational waves passing through the galaxy. These waves, produced by orbiting supermassive black holes in distant galaxies, stretch and compress space, slightly changing the distances between Earth and the pulsars, and thus the pulse arrival times. Recently, multiple pulsar timing array collaborations announced evidence for gravitational wave background, a sea of low-frequency gravitational waves pervading the universe. This detection opens a new window on cosmic history, allowing us to observe supermassive black hole mergers across the universe and probe the structure of space-time itself. Fact 70. Black holes are the ultimate stellar endpoints. When the most massive stars die, even neutron degeneracy cannot support the core. Gravity crushes matter into a black hole, an object so dense that nothing, not even light, can escape once it crosses the event horizon. They're invisible, except for their effects on surrounding matter. A black hole is defined by its event horizon, the boundary beyond which escape is impossible. Inside the event horizon, all paths lead inexorably to the singularity at the center, a point where density becomes infinite, and the laws of physics, as we understand them, break down. We cannot see inside a black hole. General relativity predicts that time stops at the horizon, as viewed from outside, and the interior is causally disconnected from the external universe. Stellar mass black holes, formed from the deaths of massive stars, typically have masses between 5 and 50 times the Sun's mass, though more massive examples exist. They're scattered throughout the galaxy, remnants of the most massive stars that have lived and died over billions of years. Detecting isolated black holes is nearly impossible. They emit no light, and space is so vast that the chance of one passing near enough to Earth to produce observable effects is vanishingly small. But black holes in binary systems can be detected. If a black hole orbits a normal star, it can pull gas from the star, forming an accretion disk. The gas heats up as it spirals inward, emitting X-rays before crossing the event horizon. These X-ray binaries are among the brightest X-ray sources in the sky, allowing us to study black holes indirectly. Another way to detect black holes is through gravitational waves. When two black holes orbit each other, they emit gravitational waves, losing energy and spiraling inward. Eventually, they merge in a violent collision that sends powerful ripples through space-time. The LIGO and Virgo detectors have observed dozens of these mergers, revealing a population of black holes more massive than expected, and providing direct confirmation that black holes exist and behave as general relativity predicts. Black holes are not cosmic vacuum cleaners that suck in everything around them. From a distance, their gravity is no different from any other object of the same mass. If the Sun were suddenly replaced by a black hole of the same mass, Earth's orbit would not change at all. The danger comes only if you venture close to the event horizon, into the region where gravity becomes strong enough that escape is impossible. There, space and time are so warped that the normal rules cease to apply. Fact 71. Stellar mass black holes likely number in the millions. Formed from the deaths of massive stars throughout the galaxy's history, these compact objects drift through space, detectable only when they interact with nearby matter. Most are invisible and isolated, dark points of intense gravity scattered throughout the Milky Way. Estimates suggest the Milky Way contains somewhere between 100 million and 1 billion stellar mass black holes. The uncertainty is large because isolated black holes are effectively invisible. We can only detect them if they happen to be in binary systems where they accrete matter, or if they pass in front of a background star and gravitationally lends its light, or if they merge with another compact object and emit gravitational waves. Most black holes do none of these things. They drift silently through the galaxy, invisible ghosts of dead stars. The spatial distribution of black holes probably mirrors that of massive stars and their remnants. They're more common in the disk, where massive stars form, and may be concentrated toward the inner galaxy where stellar density is higher. Some black holes have been kicked to high velocities by asymmetric supernova explosions, or by recoil from gravitational wave emission, sending them into the halo or even out of the galaxy entirely. The population of black holes evolves over time. In the early galaxy, when star formation rates were higher, and the first generations of massive stars were forming and dying, black hole formation rates were probably higher. Today, with lower star formation rates and fewer massive stars, new black holes form less frequently, but the old ones remain, accumulating over billions of years. Finding isolated black holes is a major goal of astronomy. Micro-lensing surveys, which monitor millions of stars looking for brief brightenings caused by a foreground object passing in front, have detected a few candidates. Future space telescopes with exquisite sensitivity may be able to detect black holes through their gravitational lensing effects or through accretion of interstellar gas. Each detection adds to our census of these invisible objects and helps us understand the full life cycle of massive stars. Fact 72. Hypervelocity stars are being ejected from the galaxy. Occasionally, stars receive such a powerful gravitational kick that they exceed escape velocity and are flung out of the Milky Way entirely. Some are accelerated by close encounters with the central black hole. Others are slingshot away by three-body interactions or supernova in binary systems. The fastest hypervelocity stars move at speeds exceeding 1,000 kilometers per second relative to the galaxy, fast enough to escape the Milky Way's gravity entirely. These stars are on one-way journeys into intergalactic space, never to return. They'll spend eternity drifting through the vast voids between galaxies, isolated lights in the darkness. The most common mechanism for creating hypervelocity stars involves the supermassive black hole at the galactic center. A binary star system wanders too close. The intense tidal forces from the black hole rip the binary apart. One star falls toward the black hole, captured by its gravity. The other star is flung outward at high speed, carrying away the binary's orbital energy. This process, called the Hill's mechanism, after the astronomer who first proposed it, can produce stars with velocities of several thousand kilometers per second. Other mechanisms can also create hypervelocity stars. In dense star clusters, three-body encounters can eject stars at high speeds. Supernova explosions in binary systems can kick the surviving companion. The explosion is often asymmetric, giving the neutron star or black hole remnant a kick, and the binary can be disrupted, sending the companion flying. Hypervelocity stars have been detected through surveys that measure stellar velocities by combining proper motion across the sky, with radial velocities, motion toward or away from us. Astronomers can calculate three-dimensional velocities and identify stars moving faster than the galactic escape velocity. Dozens of candidates have been found, and their trajectories traced back to origins in the galactic center or in the disk. These stars are cosmic outcasts, ejected from their homes by violent encounters, now traveling alone through the universe. They remind us that even in the relatively stable environment of a galaxy, catastrophic events can alter individual fates, sending stars on unexpected journeys across vast distances. Fact 73. Rogue planets drift through the galaxy without stars. Not all planets orbit suns. Some were ejected from their birth systems or formed independently in space. These lonely worlds drift through the darkness, warmed only by internal heat, invisible wanderers between the stars. There may be billions of them scattered throughout the galaxy. Rogue planets are difficult to detect because they emit very little light. They don't have a star to illuminate them, and they're too small to sustain fusion. They shine only with the faint glow of their own internal heat, primarily in the infrared, and they're incredibly dim. Despite this, several rogue planets have been detected through microlensing, where the planet's gravity bends and magnifies the light of a background star. These detections suggest that free-floating planets are common, possibly as numerous as stars or even more so. Rogue planets can be ejected from their birth systems through gravitational interactions with other planets or passing stars. In the chaotic early history of a planetary system, when planets are still migrating and orbits are unstable, close encounters can fling planets outward. If a planet gains enough velocity, it can escape the star's gravity entirely, becoming a rogue. Alternatively, some rogue planets may never have orbited a star. In the process of star formation, if a collapsing clump of gas is too small to ignite fusion, it becomes a brown dwarf or even a planetary mass object. If such objects form in isolation or are ejected before they can be captured by a star, they become free-floating worlds. These rogue planets are cold and dark, receiving no warmth from a star. Any heat they have comes from radioactive decay in their cores or from leftover heat from their formation. Some might have thick atmospheres that trap heat, maintaining surface temperatures above absolute zero. Others might be frozen solid, ice worlds drifting through the void. Could such planets host life? It seems unlikely, but not impossible. If a rogue planet has a thick atmosphere and strong geothermal activity, subsurface oceans might exist, kept liquid by internal heat. Life, if it could arise in such conditions, would exist in eternal darkness, fed by chemical energy rather than sunlight. It's speculative, but the universe is full of surprises. Fact 74. The galaxy's habitable zone is a broad region. Just as planets have habitable zones around their stars, the galaxy may have regions more conducive to life. Too close to the center brings radiation and gravitational chaos. Too far out and heavy elements are scarce. Earth orbits in a sweet spot, a galactic neighborhood where conditions are relatively stable. The concept of a galactic habitable zone was proposed to explain where in the Milky Way conditions might be best for life. Near the galactic center, several factors work against life. The density of stars is much higher, increasing the chance of close encounters that could disrupt planetary systems. Supernovae are more frequent, bathing nearby systems in radiation that could strip away atmospheres or cause mass extinctions. The supermassive black hole, during active phases, floods the inner galaxy with high-energy radiation. And gravitational perturbations are more common, potentially destabilizing planetary orbits. In the outer galaxy, different problems arise. Star formation has been less active, so there's been less enrichment with heavy elements. Planets, if they form, might be smaller and gas-poor, lacking the materials needed for complex chemistry. The stars themselves are metal-poor, which might affect their planetary system's properties. The galactic habitable zone is thought to lie in a broad annulus, a ring-shaped region between about 15,000 and 30,000 light-years from the center. Earth, at about 26,000 light-years, sits comfortably within this zone. Here, heavy elements are abundant enough for rocky planets to form. Star density is moderate, reducing the risk from close encounters in supernova, and the environment is relatively stable, allowing life time to evolve without constant catastrophic interruptions. Of course, this is a probabilistic argument. Life might exist in other regions, or the criteria might be different than we think. But the idea of a galactic habitable zone provides a framework for thinking about where to search for life in the galaxy and what factors might make some regions more favorable than others. Fact 75. Our location may have been important for life's development. The Sun orbits in a relatively quiet region between spiral arms, avoiding frequent encounters with supernova and dense star clusters. This stability may have given Earth the billions of years of relative peace needed for complex life to evolve without repeated catastrophic disruptions. Life on Earth took a long time to develop. Simple, single-celled organisms appeared fairly quickly, within a billion years or so of the planet's formation. But complex, multicellular life took much longer, only appearing in abundance about 600 million years ago. Intelligence and technological civilization are even more recent. This long timeline suggests that stable conditions over billions of years may be necessary. Frequent catastrophes could reset the evolutionary clock, preventing complexity from accumulating. Earth has experienced mass extinctions, events where large fractions of species died out, but these have been relatively rare, occurring every few tens of millions of years. Between extinctions, life has had long periods to diversify and evolve. If Earth were located in a region with more frequent supernova or other disasters, mass extinctions might occur too often for complex life to gain a foothold. The Sun's orbit through the galaxy may have contributed to this stability. We orbit in a region between major spiral arms, in the Orion Spur. This location means we don't constantly pass through the dense, active regions of the arms, where massive stars are common and supernova frequent. We also orbit at a radius where the orbital speed roughly matches the rotation speed of the spiral pattern, the co-rotation radius. This means we spend more time between arms and less time crossing through them, reducing our exposure to hazards. Additionally, the Sun's vertical oscillation through the galactic plane is currently carrying us slightly above the midplane. This may reduce exposure to whatever hazards exist in the denser central regions of the disk. All these factors together may have created an unusually stable environment, a cosmic safe haven where life could evolve without constant interruption, ultimately leading to the appearance of intelligence and civilization. Fact 76. The galaxy experiences periodic spiral arm crossings. As the Sun orbits, it occasionally passes through spiral arms where star density is higher. These crossings happen roughly every 100 million years and may expose Earth to increased radiation from nearby supernova or gravitational perturbations that disturb the outer solar system. Fact 77. Some researchers have linked spiral arm crossings to mass extinctions. Though controversial, a few studies suggest correlations between Earth's passage through spiral arms and periods of increased extinction rates. The mechanisms would involve cosmic rays, climate disturbances, or comet impacts triggered by gravitational perturbations. The evidence is not conclusive, but it's an intriguing possibility that the galaxy's structure might influence life on Earth. When the solar system passes through a spiral arm, the local density of stars and gas increases. This means more nearby supernova, which could increase the flux of cosmic rays reaching Earth. Cosmic rays can affect Earth's atmosphere, potentially influencing climate or damaging the ozone layer. Gravitational perturbations from passing stars could disturb the Oort cloud, the distant reservoir of comets surrounding the solar system, sending some comets plunging toward the inner solar system where they might impact Earth. Fact 78. The Sun oscillates vertically through the galactic plane. Our star doesn't orbit in a perfect flat circle. It bobs up and down, passing through the midplane every 30 to 35 million years. This vertical motion is caused by the galaxy's gravitational field, pulling the Sun back toward the disk's center each time it strays too far above or below. Currently, the Sun is slightly above the galactic midplane and moving upward. In about 15 million years, it will reach its maximum height above the plane, then fall back down, crossing the midplane in about 30 million years. This oscillation has been going on throughout the Sun's lifetime, a gentle bobbing motion superimposed on its larger orbital path around the galaxy. Some researchers have speculated that these crossings of the galactic plane might correlate with mass extinctions on Earth, since the midplane has the highest density of matter, and thus potentially more hazards. However, the evidence for such a correlation is weak and disputed. Fact 79. The Milky Way's rotation curve is flat. According to Newtonian gravity, stars farther from the center should orbit more slowly, just as outer planets move more leisurely than inner ones. But observations show the rotation speed stays roughly constant far into the outer disk. This unexpected flatness is strong evidence for dark matter. In our solar system, Mercury orbits the Sun at about 48 kilometers per second, while Neptune orbits at only 5 kilometers per second. The orbital velocity decreases with distance, following Kepler's laws. This is what we'd expect for objects orbiting in the gravitational field of a central mass. But in the Milky Way and other galaxies, the rotation curve doesn't decline in the outer regions. Instead, it stays flat or even rises slightly. Stars tens of thousands of light years from the center orbit at roughly the same speed as stars much closer in. This can only be explained if there's much more mass than we can see, distributed in a large halo around the galaxy. That mass is dark matter. Fact 80. Dark matter must form a vast halo around the galaxy. To explain the flat rotation curve, an enormous reservoir of invisible mass must surround the Milky Way. This dark matter halo extends far beyond the visible disk, potentially several 100,000 light-years into space, outweighing all the stars and gas combined. The dark matter halo is thought to be roughly spherical, much more extended than the flat disk of visible matter. It dominates the galaxy's gravitational field in the outer regions. Within the solar circle, at our distance from the center, visible and dark matter contribute roughly equally to the local gravitational field. But farther out, dark matter increasingly dominates. The halo may extend 500,000 light-years or more from the galactic center, though the exact extent is uncertain. At these distances, there are very few stars to trace out orbits, making measurements difficult. Satellite galaxies provide some constraints. Their motions reveal the gravitational field they're moving through, allowing estimates of the total mass out to large distances. Fact 81. We still don't know what dark matter is. Despite decades of experiments, the true nature of dark matter remains unknown. It could be exotic particles, primordial black holes, or something else entirely. Whatever it is, it doesn't interact with light or ordinary matter except through gravity, making it incredibly difficult to detect directly. The leading hypothesis is that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass but interact very weakly with ordinary matter, passing through it like ghosts. Experiments deep underground try to detect the rare occasions when a WIMP collides with an atomic nucleus, but so far, no confirmed detections have been made. Another possibility is axions, extremely light particles that could be produced in vast numbers in the early universe. Other exotic ideas include primordial black holes, formed in the moments after the Big Bang, or modifications to gravity itself that would eliminate the need for dark matter. Each idea has strengths and weaknesses, and the mystery remains unsolved. Fact 82. The galaxy's total mass is uncertain. Because so much mass is dark and invisible, measuring the Milky Way's total weight is challenging. Estimates range from around 800 billion to 1.5 trillion solar masses. Better measurements of stellar orbits in the outer galaxy and satellite motion may help refine these numbers. The uncertainty comes from several sources. First, we need to measure how fast objects orbit at large distances, which requires knowing their distances and velocities precisely. Both are difficult to measure for faint, distant objects. Second, we need to model the distribution of dark matter, which we cannot observe directly. Different assumptions about the dark matter profile lead to different mass estimates. Recent measurements using satellite galaxies, stellar streams, and the kinematics of halo stars have begun to narrow the range. Most estimates now converge on a total mass of about 1 to 1.5 trillion solar masses within a radius of about 600,000 light-years, with considerable uncertainty remaining. Fact 83. The Milky Way may be heavier than Andromeda. For years, astronomers thought Andromeda was the more massive galaxy. But recent studies suggest the Milky Way's dark matter halo may be more extensive, potentially making us the heavyweight of the local group. This matters for predicting how the future merger will unfold. Early estimates suggested Andromeda was 2 to 3 times more massive than the Milky Way. But these estimates were based on uncertain measurements of both galaxies' properties. As measurements improved, the Milky Way's mass estimates increased. Now, some studies suggest the two galaxies have comparable masses, or even that the Milky Way might be more massive. If the Milky Way is indeed more massive, it would affect the dynamics of the future collision. The more massive galaxy would dominate the merger, with the less massive one being disrupted and absorbed. The final product would be more influenced by the Milky Way's properties than Andromeda's. Fact 84. Gas inflows from the cosmic web feed the galaxy. The Milky Way doesn't exist in isolation. Tendrils of gas from the intergalactic medium flow inward along filaments in the cosmic web, providing fresh material for continued star formation. These cool flows sustain the galaxy's growth over cosmic time. The cosmic web is the large-scale structure of the universe, formed by gravity over billions of years. Galaxies lie along filaments of dark matter and gas, with vast voids between them. Gas flows along these filaments toward galaxies, accreting onto them and fueling ongoing star formation. These flows are difficult to observe directly because the gas is diffuse and hot, emitting primarily in ultraviolet wavelengths that are absorbed by Earth's atmosphere. But simulations and indirect observations suggest they're an important source of fresh gas for galaxies, helping to sustain star formation long after the galaxy's original gas supply would have been exhausted. Fact 85. The galactic fountain cycles gas between disk and halo. Supernova and stellar winds heat gas and drive it upward into the halo where it cools and eventually falls back down. This circulation helps regulate star formation, redistribute heavy elements, and maintain the galaxy's structure over long timescales. The galactic fountain operates on timescales of tens to hundreds of millions of years. Hot gas blown out of the disk by supernova rises into the halo, cools as it expands, and then falls back under gravity. Along the way, it mixes with other gas, redistributing the heavy elements created in stars throughout a larger volume. This process helps explain why even the halo contains some enriched gas, despite being populated primarily by old metal-poor stars. The fountain also regulates star formation. By removing gas from the disk, it temporarily reduces the fuel available for new stars. When the gas returns, it can trigger new bursts of star formation. This self-regulating cycle may help explain why the galaxy's star formation rate has remained relatively steady over long periods. Fact 86. Hot gas in the halo glows in X-rays. The galactic corona, a diffuse halo of million-degree gas, surrounds the disk. Though incredibly thin, it contains significant mass and energy. This hot gas is heated by supernova, stirred by stellar winds, and mixed by the galaxy's rotation. It's visible only in X-ray wavelengths. The existence of this hot halo has been confirmed by X-ray observations that detect diffuse emission around the galaxy. The gas is so hot that atoms are stripped of most of their electrons, and the remaining ions emit X-rays as they're excited and de-excited by collisions. The corona may contain as much mass as all the stars in the disk, though it's spread over an enormous volume. Understanding the corona is important for understanding the galaxy's overall mass budget and how gas flows in and out of the disk. Fact 87. The galaxy's magnetic field aligns with spiral arms. Observations show that the Milky Way's large-scale magnetic field follows the spiral structure, threading along the arms and helping to shape the flow of gas and cosmic rays. This field is generated by complex processes involving the rotation of ionized gas in the disk. The galactic magnetic field is maintained by a dynamo process. The rotation of the disk and the turbulent motions of ionized gas generate electric currents, which in turn create magnetic fields. Over time, these fields are amplified and organized into the large-scale structure we observe. The field strength is only a few microgauss, incredibly weak, but over galactic distances it has significant effects. It provides pressure support to gas clouds, affects how cosmic rays propagate, and influences the structure of the interstellar medium. Fact 88. Dust grains in the galaxy contain complex organic molecules. Analysis of interstellar dust reveals carbon-based compounds including amino acids and other prebiotic molecules. These building blocks of life are widespread, created in stellar atmospheres and cold molecular clouds, then scattered throughout the galaxy, where they may seed new planetary systems. Observations of molecular clouds have revealed a rich chemistry. Over 200 different molecules have been detected in space, including water, ammonia, methanol, formaldehyde, and more complex organic molecules like amino acids and even sugars. These molecules form on the surfaces of dust grains, where atoms stick and react in the cold environment. The dust grains act as catalysts, bringing reactants together and providing a surface for reactions that would be unlikely in the gas phase. When new stars and planets form from these clouds, they inherit this chemistry. Comets and asteroids carry these molecules into planetary systems, potentially delivering the building blocks of life to young planets. This suggests that the ingredients for life are common in the galaxy, scattered widely through the interstellar medium. Fact 89. Comets may have delivered water to Earth. Many comets originate in the outer solar system, but their composition reflects the interstellar cloud from which the Sun formed. If those clouds contained water ice and organic compounds, comets could have delivered these materials to Earth early in its history, potentially contributing to the origins of life. Earth's water is a mystery. The planet formed close to the Sun, where temperatures were high and water should have been scarce, yet Earth has vast oceans. One explanation is that water was delivered after the planet formed, by impacts from comets or water-rich asteroids from the outer solar system. Evidence for this comes from measuring the isotopic composition of water in comets and comparing it to Earth's oceans. Some comets have water that matches Earth's composition, supporting the delivery hypothesis. Others don't match as well, suggesting multiple sources may have contributed. Fact 90. The building blocks of life are common in the galaxy. Water, carbon, nitrogen, oxygen, and other essential elements are abundant. Organic molecules form naturally in space. The chemical ingredients for life appear widespread, suggesting that if the right conditions arise, life might emerge in many places throughout the Milky Way. This realization has transformed our understanding of life's place in the universe. For much of history, life was thought to require special, rare conditions. But modern astronomy has shown that the ingredients are common. Water is one of the most abundant molecules in the universe. Carbon, the backbone of organic chemistry, is created in stars and dispersed widely. Complex organic molecules form naturally in molecular clouds. Planets are common, with most stars hosting planetary systems. Some of these planets orbit in habitable zones where liquid water could exist. The question is no longer whether the ingredients for life exist elsewhere, but whether life actually arises when the ingredients are present, and if so, how commonly. Fact 91. We don't know if we're alone. Despite decades of searching, we've found no confirmed evidence of extraterrestrial life. The galaxy is vast, and we've examined only a tiny fraction of it. Whether life is common or rare remains one of the deepest unanswered questions in science. The search for extraterrestrial intelligence, or SETI, has been monitoring the sky for radio signals or other signs of technological civilizations for over 60 years. Despite examining millions of stars, no confirmed alien signals have been detected. This doesn't mean life doesn't exist elsewhere. It might mean that technological civilizations are rare, or that they don't broadcast signals we can detect, or that we haven't searched long enough or in the right way. The question of extraterrestrial life encompasses both simple microbial life and complex intelligent life. The latter is harder to detect but easier to define. Simple life might be common but difficult to observe at interstellar distances. We can only detect life on planets around other stars through indirect means, like analyzing their atmospheres for biosignature gases. Fact 92. The search for extraterrestrial intelligence continues. Projects like SETI scan the skies for artificial signals that might indicate technological civilizations. So far, silence. But the search continues, using increasingly sophisticated methods to listen for messages from other inhabitants of the galaxy, if they exist. Modern SETI searches have expanded beyond radio. Optical SETI looks for brief laser pulses. Some projects search for technosignatures, signs of advanced technology like Dyson spheres or artificial structures. Others look for anomalies in exoplanet data that might indicate artificial modifications. The search is challenging because we don't know what to look for. We base our searches on what a human civilization might do, but aliens might communicate in ways we haven't imagined. Still, the search is worth conducting. If we find even one signal, it would revolutionize our understanding of life and our place in the universe. Fact 93. Exoplanets are abundant throughout the galaxy. Observations show that most stars host planetary systems. Thousands of exoplanets have been discovered, ranging from hot gas giants to small rocky worlds. Some orbit in their star's habitable zone, where liquid water could exist on their surfaces. Planets are the rule, not the exception. The Kepler Space Telescope and other planet-hunting missions have revealed that planets are incredibly common. Statistical studies suggest that on average, every star in the galaxy hosts at least one planet. Many have multiple planets. This means the Milky Way contains hundreds of billions of planets, a staggering number. These planets come in enormous variety. Hot Jupiters orbit close to their stars, tidally locked with permanent day and night sides. Super-Earths, rocky planets larger than Earth, orbit both sun-like stars and red dwarfs. Ice giants, lava worlds, ocean planets, all have been discovered or inferred. The diversity is astounding and challenges our theories of planet formation. Fact 94. Some exoplanets may be habitable. A subset of discovered worlds orbit at the right distance from their stars for liquid water to persist. Whether they actually host life depends on many factors, including atmosphere, geology, and chemistry. But the possibility that some of these worlds might harbor life is tantalizing. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures allow liquid water to exist on a planet's surface. For sun-like stars, this zone lies roughly between the orbits of Venus and Mars. For cooler red dwarf stars, it's much closer. Several confirmed exoplanets orbit within their stars' habitable zones. Some are rocky, roughly Earth-sized worlds. Others are larger, possibly ocean worlds covered entirely in deep water. Whether any are actually habitable depends on factors we can't yet measure. Do they have atmospheres, magnetic fields to protect against radiation, the right chemistry, active geology to recycle nutrients? These questions will require new generations of telescopes to answer. Fact 95. The galaxy has a metallicity gradient. Stars near the galactic center tend to be more metal-rich than those in the outer disk. This gradient reflects the history of star formation and chemical enrichment. The inner galaxy has cycled through more generations of stars, producing more heavy elements with each cycle. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium. Higher metallicity means more heavy elements. The gradient exists because star formation has been more active in the inner galaxy. More stars means more supernova, which means more heavy elements scattered into the interstellar medium. Over time, the inner galaxy has become progressively more enriched. The outer galaxy, with lower star formation rates, has enriched more slowly. This gradient has implications for planet formation. Rocky planets require heavy elements. In metal-poor regions of the outer galaxy, planets might be smaller or rarer. In the metal-rich inner galaxy, planets might be more common and more massive. Fact 96. Metal-poor stars are fossils from early times. Stars with very low abundances of heavy elements formed when the galaxy was young, before many generations of supernova had enriched the gas. By studying these ancient stars, astronomers peer back to the Milky Way's infancy, learning about conditions in the early universe. The most metal-poor stars have less than 1/10,000th, the iron abundance of the Sun. Some have less than 100,000th. These stars formed from nearly pristine gas, only slightly enriched by the very first generation of stars in the universe. By analyzing their compositions in detail, astronomers can learn about those first stars. What elements did they produce? How massive were they? How did they die? The metal-poor stars preserved this information in their atmospheres, carrying the chemical fingerprints of the first stellar generation. Fact 97. The Gaia spacecraft is mapping the galaxy in unprecedented detail. This European Space Agency mission has measured positions, motions, and brightnesses for more than 1 billion stars, creating the most precise three-dimensional map of the Milky Way ever made. Each data release revolutionizes our understanding of the galaxy's structure and history. Gaia launched in 2013 and has been scanning the sky ever since, measuring each star's position repeatedly to track its motion. The precision is extraordinary. Gaia can measure positions to within micro-arc seconds, equivalent to measuring the width of a human hair from 1,000 kilometers away. This allows astronomers to trace stellar orbits, identify streams from disrupted satellite galaxies, map the spiral structure, measure the warp of the disk, and much more. Gaia has also measured distances to millions of stars using parallax, providing a three-dimensional map of our cosmic neighborhood. It has discovered thousands of asteroids, measured the masses of binary stars, and identified countless new stellar remnants and exotic objects. Fact 98. Gaia has revealed the galaxy's chaotic history. By tracing stellar orbits backward in time, Gaia's data shows evidence of multiple ancient mergers. Stars from absorbed dwarf galaxies still move in coherent streams, their orbits preserving the memory of collisions billions of years ago. The Milky Way's past was violent and dynamic. One major discovery from Gaia was the identification of the Gaia-Enceladus merger, a collision with a dwarf galaxy about 10 billion years ago that may have deposited tens of millions of stars into the Milky Way's halo and thick disk. Other ancient mergers have also been identified. By studying the orbits and compositions of stars, astronomers can group them into families that originated from the same parent galaxy. Each merger adds to the Milky Way's mass and complexity, leaving behind signatures we can still detect today. Fact 99. The galaxy will continue evolving for billions of years. Star formation will gradually slow as gas is consumed or expelled. The merger with Andromeda will reshape everything. Billions of years from now, the Milky Way will look very different, perhaps transformed into a large elliptical galaxy, its spiral arms long vanished. The future of the Milky Way is one of transformation. Star formation will continue for another several billion years, but at a declining rate. The merger with Andromeda in about 4.5 billion years will dramatically reshape both galaxies. The spiral structures will be destroyed, the disks stirred and puffed up into a more spheroidal shape. After the merger, the combined galaxy will likely be a large elliptical, dominated by old red stars with little gas left for new star formation. It will be a quiet, mature system, very different from the active spirals that created it. Fact 100. Eventually, star formation will cease. Given enough time, the galaxy will run out of gas to form new stars. Existing stars will age and die. Red dwarfs will burn for trillions of years, but eventually, even they will fade. The galaxy's future is one of slow decline into darkness, though that lies incomprehensibly far ahead. In the very distant future, tens or hundreds of billions of years from now, the merged Milky Way galaxy will have exhausted its gas supply. No new stars will form. The stellar population will consist entirely of long-lived low-mass stars and stellar remnants, white dwarfs, neutron stars, and black holes. Over trillions of years, even the low-mass stars will exhaust their fuel and fade. Eventually, perhaps 100 trillion years in the future, the galaxy will contain no shining stars at all, only cold remnants drifting through the dark. The universe will have entered its final age, the degenerate era, where only remnants remain. Fact 101. We are made of the galaxy, and the galaxy is made of stardust. Every element in your body except hydrogen. was forged in stars. You are assembled from material that has cycled through the galaxy for billions of years, through stars, through space, through clouds, and now briefly, through you. You are not separate from the Milky Way. You are part of its continuing story. This is perhaps the most profound fact of all. The atoms in your body have an ancient history. They were created in the cores of stars or in supernova explosions billions of years ago. They drifted through space, became part of molecular clouds, were incorporated into the sun and earth, and eventually found their way into you. The calcium in your bones was created in a dying star. The iron in your blood was forged in a supernova. The oxygen you breathe was fused in stellar cores. You are quite literally made of the galaxy. And when you die, those atoms will return to the Earth, and eventually, over unimaginable spans of time, back to the galaxy. You are a temporary pattern, a brief arrangement of galactic matter that happens to be alive and conscious. For this moment, you exist. You think. You wonder. You look up at the night sky and contemplate your place in the vast universe. And in that act of contemplation, the galaxy becomes aware of itself. And now, as these 101 facts settle gently into your thoughts, let yourself drift. The galaxy turns on, vast and quiet, indifferent to our presence, yet intimately connected to our existence. Above you, even now, the Milky Way arches across the night sky, a river of light carrying billions of stories in starlight. You rest within it, small and warm, a brief spark of consciousness in the cosmic dark. The galaxy made you, and one day you'll return to it, your atoms scattered back into the great cycle. But for now, you're here, aware, resting beneath the same stars that shone on ancient Earth and will shine long after we're gone. The iron in your blood remembers supernova. The carbon in your cells remembers dying stars. The hydrogen in your water remembers the Big Bang itself. You are the galaxy experiencing itself, a small part of the whole that has awakened to wonder at the vastness it belongs to. Sleep well, wanderer. Dream of spirals and light, of dust and time, of the vast, gentle turning of the galaxy we call home. Dream of black holes and nebulae, of ancient stars and worlds being born. Dream of the cosmic web stretching across billions of light years, of clusters and voids of the universe in all its incomprehensible beauty. You are home. You are part of this. You are made of stars. Good night.